This video is meant to be the best compilation of all the hard questions, all the good ones and interesting ones that you should know and cannot miss in A-Level Edexcel PO2 paper from 2018 to 2024. So congratulations that you have found this video. So if you later on think that there are some other questions that are more difficult than any of these, you can just give me a comment. Maybe I can create a short explaining that question and put it in the description as well. You can also check the description for the resources here, the question paper, the corresponding mark schemes, and my work solutions as well. And allow me to tell you that these resources took significantly quite some time for me to just create them. So please guys, for those of you who are going to college soon, if you don't want to subscribe, at least give me a like please. For those of you who are still in year 12, you must subscribe because I'm going to be expanding the videos to cover the further maths and physics. But let me warn you that this is going to be quite a long video, but please do make sure that you have seen all of the hard questions that I handpicked. Let's dive into it. So let's start from the year June 2018. The first question seems like this is sequence and series. Now that E-like letter is called the summation sign, yeah, and it says that you should sum from the first term, which is r being 1 at the bottom there, to the 16th term, the 16 on the top, where each term is just 3 plus 5r plus 2 to the power of r, and r varies from 1 to 16 of course. All right, so it's a good idea to maybe think about each term in the brackets separately. All right, so when you have a look at two separate terms there, you will see that there is a 3, a 5r. Well, actually the 5r plus 3, this is actually a linear. All right, this is a linear, so you can sum this from the first term to the 16th term, and then you can add with the again the first to the 16 terms of 2 to the r, because 2 to the r, if you try expand out maybe a first few terms, you will see that it's a geometric sequence, and the first one is actually the arithmetic sequence. Okay, so the arithmetic sequence, the common difference here would be 5, all right, because it's the thing that is multiplying with the 5 there. Okay, and we need to figure out the first term. All right, the first term is just substituting r equaling 1 in there. So r equals 1, you get 8. So the first term is actually 8, right? Because if we want to sum up multiple terms like this, it's probably not a good idea to just get all the terms and do that manually, right? You need to use the formulae of both types of series. Now we get D as 5 and A as 8, right? And then we can just use Sn, which is in this case S16. And you should know the formula, that it is just n over 2 multiplied by 2 times the first term plus n minus 1 times the common difference 5. So there we get the summation of the first group, which is the linear sequence or arithmetic sequence. All right, and what about the second? Yeah, the second group there is the geometric series. Yeah, so if we try put r equals 1, the first term will be 2, right? And as you can see, if you put r equals 2, it's going to be 4. R equals 3 is going to be 8. So this is multiplying by 3 term on term, and that is just saying that the common ratio, which is actually also an r, not to be confused with this r here, so I'm just going to underline this r being the order of that summation there, but the actual common ratio r is 2, right? And what did I write there? Actually it should have been a equals 2, right, the first term. So if you look at the formula sheet, yeah, we can just get the formula for the sum of the geometric series, which is this guy right here. Yeah, a normal geometric series, not infinite, would just be a times 1 minus r to the n over 1 minus r, right? So we're going to use that. So Sn here, this is S16 for the other group, equal a times 1 minus r to the n, which is 16, divided by 1 minus r, which is the common ratio being 2 in this case, right? We're gonna close that. Okay, so now we just calculate all these and we should get the answer as required, right? So let's see. I'm gonna do the geometric first since it's on the right already. So 2 times 1 minus 2 to the power of 16 divided by 1. So I'm just, okay. And then plus on the left, we have 8 there times 16 plus 15 times 5. Yeah? Oh, hang on. This should be, yeah, at the bottom here, it should be, yeah, minus 1. So I'm just going to put 1 minus 2 there. And there you go. We got it. Yeah? 131,798. All right? So I'm just going to do 1 here and 2. So S16 1 plus S16 2 equals 131,798. Yeah? So my working might be a little brief here, but you should write more if you feel like you should write more. I'm just going to keep it brief. Yeah? Okay, so that's the first part there for question 4. And then the second part, let's do it. The sequence U1, 2, and 3 is defined by that. All right, so this is sequence relation, right? And then what do we have here? Un plus 1 equals 1 divided by Un. All right, so it is just saying that the next term is just 1 over the previous term. All right, it's already given us the first term. So let's when you get this kind of sequence relation question, like part II here, and you don't know where to start, and it's intriguing to see that it asks you to sum up the first 100 terms, right? Some students are just confused and don't know where to start. Well, I would say to them that how about you get the first few terms to get some idea, right? Don't panic, just get some first few terms. Actually, I don't have any idea either here, honestly. So what I would do is I'm just going to get some first few terms, right? So like U2 is already 2/3. How about U1 is already 2/3, and U2 is just 1 over 2/3, which is 3 over 2. And what about U3? Well, that is just 1 over the U2, which is also 3 over 2, so it's going to be 2/3 again. Now, do you see that this is a periodic sequence? It's going to be in a loop between 2/3 and 3/2, right? So this is periodic sequence order 2 because there are 2 unique terms in there. All right? So that means if we want to find the exact value for the sum from the first to the 100th terms, we just pair up, right? So for each set of periodic terms, we have 2/3 and 3/2. So if we do 2/3 plus 3/2, that's going to be just 2 terms. But if you repeat that, how many times you're going to repeat until you get up to the 100th term? Well, just do 100 divided by 2, right? And that is just 50 whole pairs. Okay? So 50 whole pairs, we just multiply that by 50. Yeah? Just 50 whole pairs. Okay? So, and there is no remainder here. Because, well, if there was a 1, maybe 101, then you would have just had to add the first term back in extra after you multiplied by 50 here. But not in this case, so 50 times, that's just 4 plus 9 divided by 6, okay? So that would be 50 times 13 divided by 6, right? So that's just 325 over 3. Just going to keep my answer like that. All right. So that is for the first question in June 2028. Now let's go on to the next question. Next question, number 6. Okay, so this is just algebraic method. Given that fx is that cubic function, and then a part I, we need to calculate f2. So basically f2 is just substituting 2 into all the x's. So I'm just going to write minus 3 times 2 to the power of 3 plus 8 times 2 to the power of 2 minus 9 times 2 plus 10. And then we just going to plug that into a calculator. And then we're just going to plug that into the calculator, right? So minus 3 times 2 to the 3 plus 8 times 2 to the 2 minus 9 times 2 plus 10. Yep, that's 0. Okay. So it is kind of like implying to you here that this is a factor, right? So if 2 gives you 0 here, that means x minus 2 is a factor. So x minus 2 is a factor here. A linear factor of fx then. Okay, and that would be actually the beginning of part II. Because they ask you to write the product of two algebraic factors. It's like we need to factorize this fx, right? But we already know that x minus 2, yeah, is a linear factor of fx. And this is a bonus here because I think for this one, they probably don't ask you to show, like you don't need to, if you want to do long division, I mean, they don't mind. Like they don't mind you not showing the full long division method, right? So I'm going to introduce you to the method called short division. All right, so buckle up. Short division is done by the opposite to long division. So you take this minus 2 and change it to a plus 2. So normally we would take wholly the x minus 2 to be the divisor. Now I'm just going to take 2, which is the critical value, right? It's just the thing you sub in the f2. And then you do this. Yeah, that's how we do it. And then you copy down the coefficients of the cubic function there in descending order. So starting from minus 3, of course. And if there's like a 0 coefficient, you also write them. But in this case, there is no 0 coefficient. So in order, it's just be minus 3, 8, minus 9, and 10. Okay? Now the first step is to copy down the first coefficient here. So I write minus 3. There you go. Okay? The next step is to multiply the minus 3 here to the divisor here, which is 2 times minus 3. You get minus 6 here, right? Okay? Now, instead of subtracting the second line from the first line, we add the second line from the first line. So we add 8 to minus 6, we get 2, right? And then we repeat the step. So we got to multiply that again to this thing here. We get 4. So we write 4. What do we do again? We add. Okay, so it's minus 5. And then again, we multiply 2. So minus 5 here. We get minus 10. And then we add. We get 0. And that is indicating that this is a remainder of 0. So we get another factor here. And the way you get the other factor is to just take these numbers and put them into the factor where the leading power is 1 less than the dividend here. So the dividend is the guy that we divide, which is the minus 3x to the 3. So the quotient must be 1 degree less, which is starting by x to the 2. So the first term here we put minus 3x to the 2. Well, followed by 2x because that's just 2 and the next degree, which is x, and then minus 5. And that is the quadratic factor. Yeah? So now we can write fx is, one of them we already knew earlier. It was x minus 2. And the other one we just got here, which is minus 3x to the 2 plus 2x minus 5. Yeah? And that is it. That is it. We can just leave it at that, right? We're done. Okay, so that's just part A done, yeah? For the whole part A. Now, part B, using the answer to part AII, proved that there are exactly 2 real solutions to the equation that. Okay, so in this part, we need to use the result from the earlier part, which is AII, right? And as you can notice here, well, x to the 3 becomes y to the 6, x to the 2 becomes y to the 4, x becomes y to the 2. So actually, that is just letting x be y squared. So that is just letting x be y squared, right? So x equals y squared. That means the answers to x will be the answers to y squared. And then we can get the solutions to y from that. So to use the answers to part AII, we need to just, look at the factorized form here. Now, we haven't done anything to this to see if it contains any root, right? So I'm just gonna maybe try solve this first, or at least check if there's any more answers there just by doing discriminant, right? So if we do b squared minus 4ac for this thing, we're gonna have 2 squared minus 4ac, like that. And that is just 4, that's minus 60. This is less than 0. So no roots for this factor. Okay? So that means the only answer comes from x minus 2. So the critical value is the solution, right? So 2 is the solution. That means x equals 2. That means y squared equals 2. So y is just plus or minus root 2. Will be the only solutions because there is no solution here. And we have proven that. Okay? Okay, so only 2 solutions. Okay, that's it. Now, part C. Deduce the number of real solutions for 7 pi less than theta less than 10 pi to the equation this. Alright, so this is a trigonometric equation, and again, if you notice, it is just kind of like the same equation again, same form, I mean, at least. But this time, well, it's like a minus, right? It's a minus. So it's just, well, it's the same thing. It's just minus fx there. If you do minus fx, it's just 3x cubed minus 8x squared plus 9x plus 10. Yeah? Minus 10, sorry. And then that is just the trig form there. Okay? So we do, and this is equal to 0. We have also the same root, right? This is just, if you remember the factorized form we got earlier, it's just x minus 2. Actually, I don't remember, so let's go up. We taking the minus out, right? So that would just be 3x squared minus 2x plus 5 equals 0. Same thing, actually. All right? Because we multiply by minus 1 there. So I'm just going to say that, well, this is when x equals 10 theta, right? We're going to use the solutions from the x again. All right? So the same case here, x equals 2, again, just 1. And then we solve the trig equation. Now, but first thing first, very important actually, the range is not a typical range, 0 to 2 pi. This is 7 pi to 10 pi, right? So you got to be careful there. Well, we don't need to modify the range because this is just x equals 10 theta. So we're just going to solve this equation, okay? So in my opinion, I would like to get what's called the principal angle first. So the principal angle is just gotten by doing arctan that thing. But if that thing is a negative, then we just take the sign out and just do that. This angle will be important because when you do the cast diagram, which is the method that I'm using here, and when you draw whatever line you want, it's going to be these little angles that make with the x-axis. All right? So these are all physically alpha, the physical size of that angle. If it's a positive or negative, we just figure that out. I'm just going to show you as well. But then, okay, let's get the angle first. And we are answering in radians. Okay, so radian arctan 2. And that is just 1.107149. 107 149, right? Okay, I'm just going to stop there. Hang on, let me just check. Yeah, 149. Now, note that actually it asks for the number of real solutions, right? So we probably don't need to give out all the actual solutions to theta there. We just tell it how many solutions there are. Well, let's try think about the range of the theta here. It's starting from 7 pi. Where is that? Yeah. So if you start from the positive x-axis here and then sweep one round, you get 2 pi. Another round, you get in total 4 pi. Another round, you get 6 pi. And 6 pi, then you have to sweep up until this to get 7 pi. So anything after that will be included in the answer, but not beyond 10 pi. So 7 pi plus alpha will be the first answer. I'm just going to write down 7 pi plus alpha. And then for tan, it's quite easy, right? If you want to go to the next answer, the fastest way is to just add pi into the current answer, right? So the next one is 8 pi plus alpha, and the other one is 9 pi plus alpha. Now, if we add another pi, it's going to be 10 pi plus alpha, which is beyond the upper bound there. So we're not going to take that, but we need to figure out if this one is beyond 10 pi, which I don't think so, because alpha is just 1.1 and 1 pi is about 3.14. So this is still below 10 pi. So we get 3 solutions, right? So therefore 3 real solutions. All right. So just, I wrote all this because I want you to understand as well. So there you go. Yeah. And that is done for number 6. Next one, number 9. This is first principle of differentiation. Okay. And I made a video about first principle in calculus. And there is also another video where I proved that differentiate sine, you get a cos. Okay. You can check that out as well. But in this question, it asks you to prove that the derivative of cos is a minus sine. And we're going to use the information there. All right. Now let's take the first principle formula first, which is fx plus h. dfx by dx will be equal to the limit of h going to 0 of fx plus h minus f of x divided by h. Yeah? Okay, just going to write that down first. And then we're going to take that the function here, the fx, in this case, is going to be cos theta. That's our fx. So I'm going to ignore the limit of h going to 0 for now. So that means f of x plus h will be cos of theta plus h. All right? Yeah? And then minus cos of just theta, all divided by h. All right? Now, of course, we need to use the additional formula there because there is already a hint, cos a plus b. All right? So we're going to do cos theta cos h. Because this is a plus, so we're going to do a minus sine theta sine h. Yeah? And then minus a cos theta here, don't forget the last one there. All divided by h again, right? There you go. Yeah? Now, there is another hint that, when h approaching 0, we can use these. Yeah? So that is hinting that we should factorize this, right? So how do we do that? Well, if you look at the second term here, it's like you need to group so that you get cos h minus 1. So how do we do that? Well, the cos h here, we have, how about we pair up these two, right? So it's going to be cos theta and then cos h minus 1. There you go. So the cos h and minus 1 are together now. And the other pair would just be sine theta sine h still divided by h. So as you can see, we can sort of like split into two partial fractions, okay? Not the partial fraction that you do in the chapter, but when you split a fraction into two separate fractions, they call it partial fractions, all right? So if you split the h there, you're going to get one of them to be cos theta here, and this is just cos h minus 1 over h. This is multiply, yeah. And then minus, the other one would just be sine theta, and then sine h over h, yeah. So again, the limit of, you know, all of this, right? So we get that, I'm just gonna copy them here, 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 and then we're gonna apply the limit. So from what is given there, sine h over h is approaching 1. So this is approaching 1, yeah? So we're just gonna sub 1 there, and this is sine theta, still a minus. But then the cos h minus 1 all over h is approaching 0, so this is going to 0, right? So that is just big 0 there. And this is again sine minus sine theta. And now we have proven that. So therefore, the derivative of cos theta is just minus sine theta as required. And this is done by first principle of differentiation. All right? And that's it. So imagine all of the standard formulae that we know about differentiation is done by first principle actually in the past. The things we look in the table and remember, those are just the products of this whole work for all functions. All right? Next question in the same year still, number 14. A scientist is studying a population of mice on an island. The number of mice n in the population t months after the start of the study is modeled by the equation. And this is exponential function and modeling. Okay? So we get that exponential function, n equals blah, blah, blah there. And so let's do part A. Part A, yeah? Find the number of mice in the population at the start of the study. So at the start, we acknowledge that t equals 0. So n will be what? Equals 900 divided by 3 plus, well, 7 times e to the 0, right? Because the whole power goes to 0. So this is just 7, and that is just 90, right? Mental math there, not hard. Okay, so that's just the first part done. Part B, show that the rate of growth dn by dt is given by this. Now, when I saw this, yeah, I handpicked it because this is where like I have seen most students struggle to just get that formula. Okay, but first thing you need to differentiate first, yeah? Okay, so what do we do? Well, some of you guys might think, is this a quotient rule because we have a fraction there? But, you know, if you have a quotient of not two functions, this is, well, 900 is not really a function. It is a function, but it's just a constant. So you don't look at it as a one complicated function. It's just a constant. That means, yeah, before you differentiate, maybe you can look at it as 900 times 3 plus 7 e to the minus 0.25 t all to the power of minus 1. And you can do that just by using chain rule, right? Because if you want to do quotient rule, you're going to get, well, some more terms there. Maybe it's faster this way, yeah? So now we do dn by dt, yeah? And then we're just going to do chain rule. So we bring the power down to be minus 1. So that's minus 900. And then the power, we copy the whole thing first. And then the power minus 1, which is minus 2. And then multiply the chain rule, okay? The chain rule in the inner part there. So we're going to differentiate the inner part, which is 3 plus 7 e to the minus 0.25 t. Differentiating that and multiply it here. So differentiating 3, we get 0. Differentiating 7 e to the minus blah, 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 we get minus 0.25 times 7 e to the same thing, because the exponential function don't change the power there, the argument of the power, when they get differentiated or integrated. Okay, so that's it for this one. Okay, so now once you got the derivative here, right, you need to substitute. And now the way you do this is, there are two ways. the easy to think about way, but a little more algebra to do, versus the harder to think about way, but less algebra to do. Which one are you gonna go for, right? Let me show you the easier to think about first, right? Because most people will see this is, very obvious. So the expression they want you to get here doesn't have any exponential function, which is the e to the power of minus 0.25t. It doesn't have it here. That means we need to get rid of these guys or eliminate them by just substituting them with something, right? So if you look at the original function here, n equals blah blah blah, if we make e to the minus 0.25t the subject, we're gonna get like, okay, if I switch the thing, I get 900 over n and then 3 plus 7e to the minus 0.25t. Yeah? How do we get just e to be the subject here? So it's just e to the all that equals 900 over n minus 3, and then I'm going to do 1 over 7 here. Now this is the easy to think about way, and you're going to substitute this into all the e's. Well, that's not too easy in terms of algebra, but you're doing pure 2 now. You should be okay if you be careful. If you do it carefully, then you should be okay. Yeah, but let's do it the other way. We're gonna keep this first. Well, actually, one of the lines that already tells me here that this is the other way, that you can substitute wholly this term with 900 over n. Yeah, so let's do that. Minus 900 and then over 900 over n to the power of minus 2 times, this thing, I guess you need to use all that, right? So it's going to be minus 1 over 4 times 7 times this whole thing times 1 over 7 and then brackets 900 over n minus 3. Yeah, all that. Okay, I'm going to keep this around here, just for reference. And then we just simplify, right? So you got to be careful there. Now, this is actually, if you switch the thing, now let's cancel the minus out, right? And then 900 here, and the power of minus 2 will just be n over 900 to the power of 2 instead. Yeah, just switching the numerator and denominator there because we have a negative power. 7 here, cancel with that, okay? And then we have 1 over 4, 900 over n minus 3. That's it. Now we multiply everything. Well, actually, let's see. We have one of the n outside the brackets. So I'm going to do, let's actually expand this to the 2 like that. And as we can see, we have, we have 1 900, cancel with that. So we have 900 down here. And then seems like I need to keep 1200 outside there. So I'm going to split like this. So I have 1n divided by 1200. And then from that split we have, so we know that what we need to multiply in. So we have n here over 3, right? Because 900 times 4 is 3600. And then, so we know what to multiply in the brackets here. So n over 1200, and then n multiply 900 divide by 3n, that would just be 300, right? And then the other one would just be n. So that is as required. Just gonna make the brackets a little nicer like that. So that's as required. Yeah, that's it for part B. So it's tricky because the algebra is tricky here. That's why I picked it. Okay. Okay. Next, part C. The rate of growth is a maximum after t months. Okay, the rate. Now, this is also tricky because it says the rate of growth, not the n. N is the population. So if you thought that you would do dn by dt equals 0, that's not right. Because we want the dn by dt itself being the maximum. Now you have two ways. You can do the second derivative and put everything to 0 because that is the rate of change. Okay? We want the rate of growth here being maximum. That means we need to differentiate the rate of growth itself. Well, that's one way. Or you can consider the nature of this function. We want dn by dt to be maximum. All right? We want dn by dt to be maximum. Well, if you look at the nature of the function there, so if you plot dn by dt as a y-axis, right? So that's just dn by dt, and n on the x-axis, you're going to get 0 here and 300 here because you have n times 300 minus n. Think of this as a y and an x, right? So you have dn by dt on the y-axis and n on the x-axis. And this is a inverted parabola. Okay, just an inverted parabola there. That means we need to know the maximum here. Okay, we need to know the maximum there. So what do? Well, a parabola is symmetrical. So if you know that the two sides are at 0 and 300, then it's just in the middle. So here would just be n equals 0 plus 300 divided by 2, which is 150. You don't need to sweat at all doing the second derivative and put it to 0. That would be some algebra, some work there. But we got it already here that n, where dn by dt is maximum, is at 150. Okay? Now we just need to solve, this n value that we know would give the rate of maximum to the n there to solve for the t. So this is at maximum, so we put 150 equals 900 divided by 3 plus 7 e to the minus blah blah blah. And solving t there would give you the, t months, that big t there. Okay? So we're going to solve for this. And that is just switching this. We get that first. So 900 divided by 150 is just 6, right? So e to the minus 0.25t will be just 3. Subtract from 6, we get 7, and then divide by 7 there. So big T will be equal to, well, do the inverting there, is ln 3 over 7, and then divided by minus 2 over minus 0.25 there. All right, just going to move up a little bit here. Yeah. So what is that? It doesn't say exact value, so I think we're fine. Let's see. So that's going to be ln of 7 over 3, close bracket, divided by minus 0.25. Yeah, so the exact form we can also give, it's 4 ln 7 over 3. Yeah, I should have known. 4 ln 7 over 3, and that is just 3. I'm just going to go 2 decimal places, so 39 months. Like that, yeah? Okay. That's just the answer there. And then part D. State the value of P. According to the model, the maximum number of mice on the island is P. State the value of P. Right. So, I mean, the maximum number of mice, well, didn't we get it earlier? Oh, no, we didn't. So the maximum number of mice would be when the denominator getting smaller and smaller, right? The denominator getting smaller and smaller, if you look at the exponential term, well, the nature of e to the minus something, some constant, and then a variable, the nature of this you need to know, because when x tends to a large value, yeah, the e to the minus this will tend to 0. You need to know this. Well, you can try it. Put e to the minus 1,000. It's going to be some number very small, because that's just 1 over e to the very large number. So it's a fraction with a very large denominator, effectively. So we know that n its maximum, right, when t tends to infinity there, because it's going to make that term very small. So n max will be equal to 900 divided by 3 plus 0. So that whole thing will go to 0 and we get 300. Yeah, maximum value of p. Okay, so p is n max and is just that, 300. Okay, so that is just done for 14. Now this is the next year, June 2029. All right, so I'm just gonna write June 20, sorry, this is June 2019. All right, so let's have a look. Okay, so the first one is question 2 here, and this is trapezium rule. You got a table and then you need to find something, but now that I already told you, it becomes obvious. But if you read the question, the speed of the small jet aircraft was measured every 5 seconds, starting from the time it turned onto a runway until the time it left to the ground. The results are given in a table. So speed in meters per second and time in seconds. Using all this information, estimate the length of runway used by the jet to take off. That's it. So would you have thought that this is trapezium? Right? Probably not that obvious, but now for those of you who don't do physics or haven't done physics in the past in GCSE or anything, when we want to calculate the distance traveled, which is the length of runway here because it's the distance traveled by the jet aircraft. To do that, we need to find the area of speed-time graph. So if you imagine, if you were to plot the speed-time graph here for the table, so it's going to start from 2 here, and then 5, and then 10, I don't know, maybe, yeah, that's the, and then 10, and then 18, and then 28, and then 14. Okay, let's say it's like that. All right, so you want to find the total distance traveled by the aircraft. That means you need to find the area under the graph. Actually, I don't know if this is actually a curve, but if you want to estimate without knowing anything about the function of speed as a function of time, that is just the best shot to go, because you don't have any other method here. So trapezium rule then, right? So as you can see, the width of the strip is constant at 5 seconds, right? Okay, so trapezium method, area under the curve there is just 1/2 times the width of the strip, which is actually the height of each trapezium. Yeah, it needs to be kept constant, which is 5 here. And now in the big brackets here, you just go like, okay, the first and the last one added up first. So the speed of the first one and the speed of the last one is 2 plus 42. And then all other ones will be added up and multiplied by 2 altogether there. So 5 plus 10 plus 18 plus 28. And you got to be careful when you copy numbers down here. Yeah? Okay? And I'm just going to check. So 5, 10, 18, 28. Yeah, I'm happy with that. And then you're going to have to calculate all that. So this is 0.5 times the width, 5 times the first 2. So that's a 44 plus 2 times 5 plus 10 plus 18 plus 28. Yeah? Oh, that was wrong. This is not. Yep. And then 2 brackets. Yeah, so that's just everything. Let me just check. Yeah, 44, 2, 5, 10, 18, 28. Yep, 4, 1, 5 is the area. Okay, so that is just in meters there. And that's it. That's part A done. Part B, given that the jet accelerated smoothly in these 25 seconds. So I think in this case, we need to look at how speed changes over 25 seconds interval here. So if you go from the 0 second to the 5th second here, you have 2 going to 5, so that's increasing by 3. And then 5 to 10 increasing by 5. That numbers goes up, right? And then 10 to 18 goes up by 8. And then by 10. And then by 16, no, 14. So the change in speed increases. That means the acceleration also increases. That means the gradient of this is not uniform anymore now. The acceleration of this motion is also increasing. So the gradient of the graph here is also increasing. So actually I should have drawn something like, you know, like maybe like this. Okay, rather than just the one I had earlier. All right. Well, that means if we do trapezium, right? Let me make it more extreme, yeah, so that you see clearly. So what did you do? You did like this and this and this and this and this, yeah? So you are estimating the area like that. And for every line you draw between 2 points there, the line is always above, yeah? The cap of the trapezium there is always above the curve, okay? So that means you are getting more area than actuality there, okay? So, and we need to explain as well. So the trapezium, the top side of each trapezium is always above the actual curve, yeah? So this is an overestimate, yeah, because the trapezium has more area than what it actually is, yeah? Overestimate, okay? And that is just it. Let's go to the next one for this whole series here, number 5 in the same year, June 2029. Figure 3 shows a sketch of the curve with equation y equals root x. Okay, so this is again kind of similar, but now it gives you the graph, and the rectangle shown shaded in figure 3 has a height of y and width of, what is that, delta x. You can say delta x because that is a little d for a Greek version, delta. Okay, so the capital is the triangle here, but the lowercase is that. So this is delta x, and that is indicating a change in x. So that is just Riemann summation for fundamental theorem of integration. Actually, what you see down here is just kind of like the definition, the Riemann sum. Okay, Riemann sum of integration. So it is saying that you are summing one of these strips. Okay, so for each term, for each x equals something, let's say x equals 4, you're going to have that strip drawn at this around this line here, a very narrow strip. Okay, and it's so narrow that the delta x here, which is the width of the strip, is getting closer and closer to 0. If you imagine that very small strip, and they're called infinitesimal strips, if you sum them up from 0 to 9, of course you're going to have the area under the curve, and that is just integration. So this is basically integration in a more fancy way, if you like. So basically just integral, and the limits will just be 4 to 9. Square root x dx. That is just it, yeah? So that is x to the power of a half. So integrated, we get x to the power of a half plus 1 is 3 over 2. Divided by 3 over 2, we get 2 over 3. Yeah, so that's just integrating, 4 to 9. So I picked this one so that you know that this is just integration, all right, if you didn't know that, okay? I mean, it wouldn't be that hard if you knew it, right? Okay. Then, yeah, just substituting, so 2 over 3, and then this is 9 to the power of 3 over 2. I think that's 27, yeah? Okay. And then 4 to the power of 3 over 2, I think that's 8, because that's 4 to the power of 1 over 2 first, that I get 2, and then 2 to the power of 3, I get 8. So 27 minus 8 is 19, so that is just 38 over 3. Yeah, that's it. Okay, so that's it for the whole thing. That's short. Now let's do number 6, right? Number 6 is about probably domain and range and functions, right? Figure 4 shows a sketch of the graph y equals gx, where gx is all that. Okay, so this is called piecewise functions. You have you have separate cases where if x is in this range, the function looks like that, and if x is beyond that range or other ranges, then the function looks like that. Okay, so you got to be careful here because you are asked to calculate g of 0. So the first g of 0, right? So if we calculate g of 0 first, so 0 is in the range x less than equal to. Yeah, because 0 is less than 2 there, so we need to look at the first function, the top one. So we got to put x minus 2 there to the power of 2 plus 1. This is just 5, right? Yeah, and then now we need to find g of 5. Well, 5 is now greater than 2, so you need to put at the bottom function. Yeah, so that is just 4 times 5 minus 7. That is 13. Okay, so we can conclude that g of 0 will just be 13. That is part A done. Part B. Find all values of x for which g of x greater than 28. So we're just going to solve this range here, yeah? Now we got to be careful. I'll tell you. So x minus 2 to the power of 2 plus 1 greater than 28. Yeah, that's just putting gx greater than 28. Well, actually, we don't know yet because there are two functions, right? So if we look at the graph here, let me just draw that quickly. There you go. 28 is like this line. If you draw it, around there maybe. So we need to find the solutions to x, the range of solutions to x, where the function is greater than 28. So that is where the curve, like the parts of the function here, which is these, are above the dotted line, which is what I already highlighted there. Yeah, so it's this one and this one. That means it's going to happen when you go to the left from that and to the right from this. That means we need to solve for 28 equals this part and 28 equals this part separately. All right. So let's do the left wing first, which is the left wing of the function here, which is the quadratic there. So we're gonna do x minus 2 squared plus 1 equals 28. And this will give you the x value here because we equate the two lines, so they're gonna intersect there. Okay. So 1 subtract 28, we get 27. So that is just x equals minus, because we know it's going to be a negative side, square root 27 plus 2, right? Yeah. So that's, let me just double check that. 27 and then square root, take a minus, and then plus 2. Yeah. So this is a 3 root 3 plus 2. Okay. And the other one is just solving between 28 and the straight line, right? So I'm just going to do that. So putting 4x minus 7 equals 28. So that is just what? X equals 35 over 4. Yeah? And that's x2, just the other bit there, which is, this is x2, this is x1. So now the range of solutions to gx, right, will just be what? To the left of the x1 and to the right of the x2. Yeah. So x less than minus 3 root 3 plus 2, or x greater than 35 over 4. Yeah. We don't need to do a decimal there because that is an exact value. It's good for pure math anyway. So we're going to keep them like that. Okay, that is just it. Okay, for part B. Part C. The function is defined by that. C explain why h has an inverse but g does not. Okay, right. H has an inverse. if you look at the function here, this is happening at x less than 2. Okay, so the hx is actually, if we draw the graph there, is just this left wing of that gx. It doesn't take the right wing. Yeah, so this is actually the vertex at 2 there, and that's probably at 2 there at the bottom there. That's where the function changes to the other piece. So this is saying that this is not even a many-to-one function. Okay, so when you flip the thing, and let's say that is just y equals x. When you flip the thing, when you find the inverse, it's gonna look something like, I don't know, maybe like this, right? And that is still a function because it's 1-to-1. Yeah, so we can say that hx, where x less than equal to, is not a 1-to-1 function. Yeah, so it has an inverse. So any 1-to-1 function will have an inverse. But you see gx, right? Gx also includes the other piece where you have 4x minus 7 here, which is this guy. Now gx in totality is not a 1-to-1, it's a many-to-one. Yeah, is a many-to-one function. Why? What's wrong with that? Well, when you flip a many-to-one around the in the y equals x mirror, it's going to give you a 1-to-many relation. We can't say that's a function. 1-to-many, there is no function 1-to-many, right? So we call it a mapping or a relation. Yeah. So because gx is a many-to-one function, so it does not have an inverse. Just it. That's just it. Okay, just the reasoning there. Okay, so D, solve the equation, the inverse of hx equals minus 1/2. Okay, so yeah, if you look at the graph already, it's just y equals minus 1/2 is around here, so that's around there. We expect that to be positive. Now, how do we do that? Well, the easy way here is to maybe, if you write down h inverse equals minus 1/2 here, what you can do also is to, play around with the algebra of the function here. So you can move the h inverse to the other side, just like you solve the algebra, but it would become an h of minus 1/2. And that is it. That is it. That's just it. So what you're doing here is you just do the h of minus 1/2. So plugging minus 1/2 into the h function here, and you should get the answer because we are solving for x, right? So that is the x. So x equals minus 1/2 minus 2 to the power of 2 plus 1. So that is minus 5/2 to the power of 2. So it's 25/4, right? And plus 1. So I have here 29/4. That's it. Okay, sorry. I went down further a bit there. Need to go up. There you go. 29/4. That would just be the answer, which is kind of like what we expect because they intersect at somewhere here, x being positive, right? There you go. Okay, so that's just done. See, if you know how to use some trick here, it's easier. I didn't even have to solve for any equation. That is just the way to go there. All right. So question 8. Part I, find the value of that. This is some series again, I guess. Okay. Now, again, guys, if you panic when you see a sequence like this, and this is actually a series because it's a summation of terms. So from I equals 4 to infinity, that's a lot of terms, right? The first thing to do is to get the idea about what each term is. Maybe the first few terms. So r equals 4, that is the first term because it starts from r equals 4. You're going to have what? 20 times 1 over 2 to the power of 4. And then r equals 5. 20 times 1 over 2 to the power of 5. R equals 6. Just first 3 terms maybe to see the pattern. Okay? So I got that. Now as you can see, okay, let's do the calculator there. So this is 20 over 16 for the first term, and that is just what? 5 over 4, right? 20 over 16. What's the next term? Well, the next term seems like you just have an in extra multiplying by 1 over 2. So that is just 5 over 8, right? Yeah? And then also this is 5 over 16. Now you can see that to go from one term to the next, you multiply by a half. Isn't that a geometric sequence? It is. Now we have identified then that A should be the first term being 5 over 4, right? And then the R, which is the common ratio, is 1 over 2. And then whatever summation it asks you to solve, you can use the S infinity because this is to infinity. So because we now know that R is less than 1, so that is definitely valid. You can do S infinity there. So S infinity is just A over 1 minus R, right? In the formula sheet there. So 5 over 4 over 1 minus 1 over 2. So my 1 minus 1 over 2 is just 1 over 2. So you multiply 2 there, you get 5 over 2. That's it. Done. For the part I. Part I, right? Show that. That. Okay. Again. Just get some idea for the first few terms, right? So the first term n equals 1 log 5 of what? 3 over, what is that? 2. And then n equals 2 log 5 of, what is this? It's going to be 4 over 2, 4 over 3, sorry. And then when n equals 3, this is going to be log 5 of 5 over 4. You see the pattern there. Okay, now, so if you sort of like see the pattern here, yeah, if you see the pattern here, we are summing from the first term to the 48th term, okay? But if we use log properties here to just get some better idea about these whole log things, then this is just log 5 of 3 minus log 5 of 2, right? Yeah, that's the first term there. And what about the next term? This is log 5 of 4 minus log 5 of 3. Do you see something? Do you see what I'm seeing here? Because this is a negative. It can cancel that. Well, let's do the other term. Log 5 of 5 minus log 5 of 4. There you go. So if you add all of these, I'm just going to write plus here and plus here to connect all of them. You will see some cancellation, like that cancel with that, and that cancel with that. And this is going to keep going, right? And you must imagine that if you keep going in the terms, what will be left? Of course, let's say if n equals 3 is the last term, right? If n equals 3, say it's the last term, instead of 48 there, you have n equals 3 instead. So if n equals 3 is the last term, then you would have left, so that cancel with that cancel with that. Wait, hang on, sorry. That cancel with that, and that cancel with that. So you're going to have the second last term and the second term, right? Okay? So if you imagine now you keep going until the n equals 48 term, you're going to have log 5 of what? The top bit is just 50 over, what is that? 49, right? Okay? 50 and 49, that's the 48th term. So that is just log 5 of 50 minus log 5 of 49. Yeah? And again, just as we discussed, you're gonna cancel even the last term, and you have this left, right? So you just have this term and this term added up, yeah, from n equals 1 to n equals 48. Okay, so I'm just going to write here that will be equal to minus log of 5, log base 5 of 2 plus log base 5 of 50. Yeah, going to shrink the whole thing down here. We need to provide some working, maybe. So we need to see that, okay, all of the terms cancel. Maybe I'm going to tidy up the working here a little. And then put n equals 48 here and this thing here. Yeah. And then I do plus dot 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 plus. Okay, dot 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 dot. Okay. So cancel. And the left hand side, which is the thing we want, is just the sum of those two terms. Yeah. That's it. So if we simplify that, that is just log base 5 of 50 divided by 2 using another log property. Yeah, the same actually. So it's just log base 5 of 25. Well, isn't that just 2? So 5 to the power of what gives you 25? That's just 2, right? Okay. So the answer is 2 as required. We just showed that. All right. So that's done for this question. Next question. Now this is the real deal here for vectors. It might stink a little bit, yeah, for some people. Maybe not a little bit, okay? Number 10. Figure 7 shows a sketch of a triangle OAB. So let's draw some diagram first, right? So I'm just going to make a diagram here, OAB, triangle OAB, like that. And then point C is such that OC is 2 times OA. So you can't fit C in here because OC has to be longer than OA. So C has to be outside or beyond the OA part there. So I'm just going to move down and stretch, extend the length there to OC. Okay, so that's OC 2 times. So if OA is A, then AC is also A because, yeah, OC must be 2 times. So 2 times A there. Okay. Point P is another point halfway between A and B, so that's point M, a midpoint of AB. And then straight line through CM cuts OB at point N. So it's going to be that straight line there, yeah, at point N, yeah. Okay, now given that OA is A, yeah, we got that, and OB is B. So here is OB, yeah. That's vector B there. And part A, find CM in terms of A and B. Okay, CM. Now for those of you who are not proficient in vectors, when they ask you to find particular vector, this is a relative vector, yeah, from one point to another. Well, you can just think how you would walk from one point to another. This is C to M, vector CM. So you can walk on a detour. Walking directly from C to M won't help, so you walk on a detour. So for example, you can walk from C to A and A to M. That's the shortest path, right? So CM is just from C to A plus A to M. Yeah? So what is that? C to A is minus A, right? Yeah, this is minus A because A is going like that. If you go the opposite way, it should be a minus because vectors have directions. Okay. And then what is A to M? Well, A to M, we don't know yet. And it seems like we need to walk on a detour again. So from A to O and O to B. But yeah, so we need vector AB, yeah, because we know that AM is half vector AB as M is the midpoint of AB. Because M is the midpoint of AB, so vector AM is half vector AB. So we're going to write here vector AM is 1/2 vector AB. But vector AB is what? Well, vector AB is just A to O and O to B, right? Yeah, that's not hard. So that is just minus A plus B, right? That's vector AB. And then we plug that in. Yeah, we plug that in here. Okay, so that's just going to be minus a for CA, and then AM will just be plus 1/2 minus a plus b. So if you simplify that, minus a minus 1/2 a, that is just minus 3/2a, and plus 1/2 b, right? Okay, so that's part A done. Part B. Show that ON is blah blah blah. Okay, again, we're going to stick to the same concept, ON. Whatever they ask you to find, we're going to walk on a detour. Okay, so ON, not directly, so we might go from O to C straight and C to N. For each detour you take, maybe take the minimal path. So, I mean, rather than doing OA, AM, and MN, you want to do OC and CN like that. But it must be a detour, yeah? Okay, so ON is just OC plus CN. There you go. Now, OC is easy because we know it's 2A. But CN, well, CN is kind of like we have no idea about it yet. Nor do we know the ratio of anything here. So we got to make things up here. But taking from the question, you see the lambda. So lambda comes from somewhere. Well, let's think about it. If you want to do CN, but we kind of already know CM. We kind of already know CM. We can't add CM to this directly, but because point C and M and B, point C and M and N are on the same straight line. So that means these two vectors, like actually three vectors, so there's CM here and CN and MN as well, they are all parallel. Well, but because we already have CM here, but we want CN, so how about we make CN as a multiple of CM, just like that. And that multiple happens to be lambda. Well, actually, there is no way to know for sure at first. You just have to try it. So if putting lambda like this doesn't work, you can just go like, okay, let's try the other way around. So let's try lambda CN equals CM instead. See if it works. But the reason that this is likely going to work is because you already got CM. And to get CN here is just some multiple of it to be CN. And let's see, okay? So we're just going to sub lambda times the whole CM there, which is what we got in part A, like that. Okay, so this is just 2A, 2. If we merge the term A, so it's 2 plus. If you expand this, you get minus 3/2 lambda. That is just A there. And for the B, there is just one term, which is lambda over 2B. Just multiplying the lambda into the brackets, and that is what it wants, right? So if we simplify the signs here, we should get one single minus there. Okay, so that is just as required. Part C, hence proof that ON to NB is 2 to 1. All right, so okay, we have got ON already. Now we need to find something about NB, and then if we do the ratio, we should get 2 to 1. So that is just saying that if we go back to the diagram, so ON to NB here, this is 2 times this, right? So NB is like half ON, yeah? So we just aim here first that NB, we want to prove that NB is just half ON, right? Now, this is so subtle, but if you look at vector ON, right? Okay, we got it to be this expression, but if you look at vector ON, it is already in the direction of vector B. Okay? That means it has no component for vector A. It's like, okay, for example, if you go, let's say if you have coordinate system X and Y, let's say if you are on 5, 0, the Y value or the Y coordinate will be 0. It's just like this ON here. Because it's already pointed towards the right, it doesn't have any A component. Well, that means, yeah, because it doesn't have any A component, well, but the ON previously, we have this, right? So that means the 2 minus 3/2 lambda must be equal to 0. Okay, well that means we can solve for lambda here, guys. So lambda equals, moving to the right, multiplying 2, we get 4 over 3. That's the lambda there. Yeah, if lambda equals 4 over 3, then that means ON is now revealed to be no A, but then this is 4 over 6B, or 6 there, or just 2 over 3B only. So that's vector ON, guys. Yeah? Okay. Now, what about vector NB? Yeah? Vector NB is just this little guy here. Okay? Now, how do we prove that? Well, because we probably need to do NM still, and then, yeah, MB there, right? But we got lambda already, which is good. So, we're going to do NB here now. NB will just be NM plus MB, yeah. Okay, what is NM? Now let's talk about NM, right? Because NM is on the straight line CMN. Yeah, we got earlier that Cn, now Cn to Cm is lambda. Cn equals lambda, which is 2/3 Cm. Cn is shorter than Cm, yeah? Cn, wait, 2/3 Cm? Oh, sorry, I got the lambda wrong. It's not 2/3, it's 4 over 3. Yeah, Cn is 4 over 3 Cm, it's longer. So that means Cn to Cm should be, what was that? 4 to 3, right? What about if we want something to do with Nm? So Nm, wait, okay. So Cn is the whole side here. Let me draw the diagram again, yeah? So this is C, and then N here, and then M, right? So the whole Cn there is just 4 units. The Cm is just 3 units, so there are just 1 unit. There's just 1 unit for Mn here. That means Nm, vector Nm, will be equal to 1 out of 4, right, of Nc. Now, we need to take into account the direction. So because we're doing Nm here, we need to do Nc here. So it's 1 over 4 Nc, right? Not Cn. Okay? But we already got Cn, right? So Cn was this guy here, this whole thing. This is Cn. So Nc will just be 1 over 4. So Nc will just be minus lambda. Yeah, I'm going to minus this one. Yeah, negative that one. So minus lambda, 4 over 3. And then that in the brackets there, minus 3 over 2a plus 1/2 b. That is just Nm, this whole term. Plus, but Mb we already got, I think. Because Mb, don't forget that M is the midpoint of AB. So because we got here earlier that AM was this. So MB should be the same. So MB is just half times minus A plus B. So it's going to be minus 1/3 times minus 3 over 2. So that's going to be a half A there. Plus minus 1/3 times 1 over 2. That's minus 1 over 6B. Plus 1 over 2A. Plus 1 over 2B. So we have here the half A cancels there, and we have 1 over 2 minus 1 over 6. So that's going to be 3 over 6, and then minus, yeah, it's a 1/3 B, right? And this 1/3 B happens to be a half of 2/3 B, right? Yeah, I'm just trying to relate it back to this ON here. So that is just a half ON, right? So that means NB equals a half ON. So we can conclude now that ON to NB is going to be equal to 2 to 1 as required, right? And that's it, yeah, for this one. Let's have a look at the next one, question 11. Yeah. Figure 8 shows a sketch of a curve C with equation y equals x to the power of x when x greater than 0. All right. A, find by firstly taking logarithms the x-coordinate of the turning point of C. Right, so this is quite rare. It doesn't quite come out like this, but yeah, it is a possible way. Yeah, so we are gonna take ln, maybe a natural logarithm. Usually taking natural logarithm is easier, which is ln. So we do ln y equals ln x to the x. Okay, so that's just now if you use the log property on the right side, you're gonna get ln y equals x ln x. Yeah, okay. Now we want to do something with the turning point. The turning point is when dy by dx equals 0, right? But we don't know anything about dy by dx yet, and this equation is not explicit yet because it's not y in terms of x. But the way to get dy by dx in a non-explicit term like this, we can just do implicit differentiation. So we apply the operator d by dx is just to differentiate ln y respect to y first, but we do chain rule dy by dx. Yeah, so just like pretend that it were an x, but then you just put dy by dx later. So differentiating the right part is just the product rule. So because it's a product of two functions, so v du plus u dv, so just ln x. Yeah, okay, so v, well actually I did u dv, right? U dv plus v du. Yeah, just to make it, just making sure. Yeah, so that's just ln x plus 1, right? And then if we multiply the y here on both sides, we get y multiplying that, and this is just dy by dx as a subject. So if we solve dy by dx being 0, yeah, because we want the turning point there, so I'm just going to put this to 0. Well, y will go to 0, right? Y will go to 0. I mean, y doesn't go to 0. We just can cancel y there, assuming that it's greater than 0 or something. So we have ln x plus 1 equals 0. Okay, so ln x equals minus 1. That means x is e to the minus 1. All right, just invert that function there. You move ln x to the other side, you get e to the minus 1. So yeah, so the turning point is that, or 1 over e here, but that is just the x value. So y will be at 1 over e to the 1 over e. Okay, it's just weird to write it like that, but yeah, there you go there, I guess. So it's basically e to the minus 1 to the power of minus e, isn't it? Right? No, hang on. It's e to the minus 1 like this. Yeah, sorry. Okay, so if we want to simplify that, it's going to be e to the minus 1. It's just a bit weird to write, right? So the turning point here is just e to the minus 1, comma, e to the minus 1. Okay? That's it. And then this is part A. So part B, the point P alpha 2 lies on C, right? Show that 1.5 is in between alpha is in between 1.5 and 1.6. All right, so yeah, so if we plug y equals 2 into the function and then solve for the x, right? So if I put 2 equals x to the x, yeah, and then if we solve for this, so we could do like x to the x minus 2 equals 0. So if we solve for that, if we solve for this function, we're going to get the value of x, which is alpha. But it is impossible to solve by hand, maybe. So we're just going to show that the root is in between by using a numerical method, right? So I'm just going to put here first fx equals x to the x minus 2 because we want to solve for the root of fx. The fact that we equate this to 0 means that we are solving for the roots of this x to the x minus 2. So if I do like f of 1.5 and f of 1.6, And if there is a change of sign, then bingo, right? So 1.5 to the power of 1.5. Sorry, that's not 1.5. And then minus 2. Yeah, I'm getting minus 0.1628883. And the other one is just 1.6 to the power of 1.6 minus 2. Yeah, that is expectedly a positive root. 0.121251. Okay, so there is a change of sign of fx while being continuous, yeah, in the interval 1.5 and 1.6. Therefore, there is a root is in the interval 1.5 and 1.6, right? Yeah? Yeah, so we can write that exactly because it's in between. Okay. Now, next part, part C. A possible iteration formula that could be used in an attempt to find alpha is that using this formula with x1 equals 1 plus 1.5, find x4. Well, that's gonna take some time because we need to keep pressing the calculator there. So we're gonna do, just gonna use another calculator here. Okay, there. So we're gonna do 1.5 answer first, and then that is just 2 times, yeah, xn, which is answer, to the power, where's my power? Okay, to the power of 1 minus answer. So that's already my x2 equals 1.632, 3 decimal places, right? So it's 3, yeah, 1.633. If I press equal sign, it's going to store first. If I press it again, it's going to be x3. That was x2. 1.466, right? 3 decimal places. And then another time, x4 now, it's going to be 1.673. Okay. And then that's part C. I'm going to keep my calculator on here because part D describes the long-term behavior of xn. So it is asking us to just keep pressing the thing and see if it converges to something. That doesn't converge to anything. It's going to be a periodic sequence between 1 and 2. It's going to oscillate between 1 and 2. Yeah, that's the long-term behavior if we try it out. Yeah? Okay. So part D, xn will alternate the value between 1 and 2. Okay, just keep pressing the calculator there. That's not hard to describe. Next question, question 12. All right. Part A, prove that. All right. So this is not, it's subtle here. Yeah, this proof is quite subtle. Okay, we'll see. So you have a fraction, 2 fractions here. Okay, on the left part. We need to do something so that we get 2 cot 2 theta. Okay, so how about, I mean, if you feel like combining the fractions, just go with it. So okay, so the first step we get, so left hand side equals cos theta, cos 3 theta plus sine theta, sine 3 theta divided by sine theta, cos theta. All right? Yeah? Now, well, most of you might think, okay, that's hard work because 3 theta, we need to do double angle, right? Twice maybe? That's horrible, isn't it? But if you are quite familiar with the use of additional formula, don't you notice that this is theta and 3 theta, and this is also theta and 3 theta? This is a cos and cos, this is a sine and sine. Isn't that mimicking the expression of some additional formula? It's the cos A minus B formula, right? So the top bit is actually cos A, which is the left one, minus B, which is the other one, right? Well, I mean, if you swap the thing, well, let's make this positive, right? Just to avoid all the hassle there, I'm just going to do 3 theta minus theta instead, yeah? Because, I mean, you can swap the thing and it's still the same, yeah? Okay? So that's the top bit. And the bottom bit, well, okay, if you think about the top bit first, is cos 2 theta. So the bottom bit should be kind of similar, because sine theta cos theta isn't it actually the double angle of sine 2 theta, right? So sine 2 theta is 2 sine theta cos theta. This is then half of that. So it's half of the sine 2 theta, right? Okay? So yeah, keep simplifying, we get cos 2 theta divided by, well, 2 can multiply up there, so we get that, yeah? Well, cos over sine, isn't it just cot, right? So this is 2 cot 2 theta as required. Yeah, so the really tricky bit is just to know that you need to use additional formula there when you see the pattern of the angles like that, A and B. Yeah, just bear in mind. That's why you need to see this first. Hence, solve for 90 degrees less than theta less than 180. That. Okay, so this shouldn't be bad. We already have that whole thing is 2 cot 2 theta. So I'm just gonna write 2 cot 2 theta equals 4. Yeah, that whole thing there. All right. So and then we just move this. We just solve this. So I divide by 2 across. And what is that? Well, cot is just 1 over 10 2 theta, right? Equals 2. So actually 10 2 theta is just 1 over 2. Yeah? Now let's solve this, but let's modify the range first, because we have 2 theta here and not theta. So that means 2 theta, if we multiply 2 on either side, we get 180 on the left side and 360 on the right side, all right? So we know that that is the domain that we should go in. So the first and the second quadrant, nada. There's no answers in those quadrants. Okay, so this is tan of a positive value, so it's just these lines. So if the first quadrant, there isn't an answer for that, we need to go to the third quadrant here. Okay, so let's find the principal angle first again. So I'm just going to do arctan 1/2. See what I got there? Let's put this to alpha. Yeah, I'm just going to write the value down. Actually, let me not do that. Yeah, so let's just keep it as alpha, and we can talk about it in terms of alpha here. Yeah. So the first answer is in the third quadrant. Yeah, because it's greater than 180. So I'm just going to write 2 theta here equals. So the first answer is just pi plus alpha, right? Now, if you want the next answer, again, in tan, it's very easy. You just keep adding pi. Okay? So keep adding pi. Again, the next one is 2 pi plus alpha. Are we out of the range already? Yes, it seems like we are, because 2 pi plus alpha is greater than 360, isn't it? Right? It's greater than 360. So we're going to cut this answer out. So the only answer is that. Yeah, so theta is just pi plus alpha divided by 2, and that is just, let me use another one actually. Yeah. So fraction pi plus, this should be in radian. Alpha is just arctan 1/2. and then divided by 2, isn't it? Yeah, pi plus alpha divided by 2. So there is 1.80262. Okay, dot dot dot. So giving any solutions to one decimal place. Yeah, so that doesn't mean you should have more than one because it says any. So this is just that for the answer. Yeah. Now let's go to the next year, October 2020. Probably almost halfway here. Yeah. Okay, let's have a look at the first hard question. Okay, this is still trapezium, right? It's trapezium, October 2020 here. Question 1. The table below shows corresponding values of x and y for y equals that function. The values of y are given in 4 significant figures. A, use trapezium rule with all the values of y in the table to find the estimate for that. Well, this part is easy, right, guys? But this one is hand-picked because I saw the second and the third part. Well, particularly the second part. It's not too bad, but you will see later another question like this is a little trickier. Yeah, you will see. Okay, so just stick around. Yeah. So we're going to do part A quickly. Yeah, because that's just trapezium rule. So 1/2 times the width of the strip, which is 0.5 there. And then we're going to add the first, yeah, and the last one. Yeah, each of them, and then plus 2 of all the other ones added up. So 7071 plus 7746 plus 0.8165. Yeah, that's not very tidy, but you know what I mean there. Okay, so 0.5 times 5 times brackets 0.5774, yeah, plus the last one 0.8452, yeah, that should be a 0 here. Okay, almost lose a method mark there. Plus 2 times brackets 0.7071, yeah, plus 0.7746, yep, plus 0.8165 bracket. So I got that 15.3 significant figures, that's just 15.0. I'm just going to put 0475 and then 15.0 here, 3 sig figs, yeah. Let me double check everything, yeah. You can't be too careless there. So 1/2 times, ooh, yeah, I made a mistake. This should be 0.5, right? It's not 5, right? And then let me check again. So 0.5774 plus 0.8452 plus 2 times the whole brackets of 0.7071 plus 0.7746 plus 0.8165. That becomes 1.50475 instead. 1.50475, 1.50. Okay, that's just like 1/10 previous answer. Yeah, just checking. All right, that should be fine. Now part B, right? Using your answer to part A, deduce an estimate of that. Now, okay, this is important, guys. This expression here is only similar to this, but it's just out by a factor. You see, if you multiply 9 inside here, you get exactly this. But how do we use the fact that this integral is already about 1.50, right? Well, that thing, yeah, that whole thing, I'm just going to write down here, is actually I mean, if you take the 9 out from the square root, it's going to become the square root of 9. So you can write 3 instead. Yeah, because it's actually square root of 9 out, but then square root of 9 is 3, right? So it's 3 and then the same thing. There. Isn't it? Right? And that is already what we got from the trapezium estimation there. Okay, so this is actually 3 times the area that we got earlier. Okay, so this is just 4.550. Okay, that's it. You will see later that there is a trickier one than this. Part C, given that equals 4.535 to 4 significant figures. Yeah, we are quite close there. Comment on the accuracy of your answer to part B. So we just gonna maybe use do some percentage different here. So I'm just gonna do that compared to the actual there. Okay, because that is by actual integration there. So let's do that. That's fraction 4.535 minus our answer 4.50, right? And then compared to the original, the more precise one, assumingly this one, you're gonna get 0.007718, which is about 0.77%, right? And that is very small. So therefore, this is small difference. Yeah. Therefore, good accuracy. Yeah, that's it. All right, just minimal conclusion there. Okay, let's do the next one. Question 7 on the same year here, October 2020, right? Isn't it? Yeah. Figure 1 shows a sketch of the curve with equation that A show that. Okay, so this is differentiation, right? And yeah, we're gonna differentiate split. So the first term is the whole polynomial there, rational polynomial, and the other one is just ln, yeah? So dy by dx, part A, dy by dx. So the first one is a quotient of 2 functions. This is a quotient rule, all right? So it's v du, so v being the bottom one, du, so we differentiate the top bit, which is 8x plus 1. I'm just gonna not take much time here to differentiate. You guys should be okay with this. Yeah, v du, yeah, already done, minus u, which is the top bit still, dv, we differentiate the bottom bit. Let's write that in an index form like that. So differentiating that, we get 2 times 1/2 power brought down, and then x to the minus 1/2. Yeah. Okay. So, and that is all divided by what? The v squared. So that's 4x, right? And don't forget, we gotta differentiate for ln x as well. So differentiate ln x, we get 1 over x. So that's just minus 4 over x here as well. Okay. Now, yeah, seems like we can simplify. Now let's look at the top bit first. It seems like if we take the the most negative power, which is the smallest power of x, is x to the minus 1/2. So whenever you are factorizing complicated looking long algebraic term like this, you should take like the x with the least power. The least meaning most negative. So this is x to the minus 1/2. So I'm going to take that out. Note that this cancel, right? Let's see. Okay. X to the minus 1/2 out, and then big bracket. Okay, so that is going to be left with what? This used to be x to the half. If you take x to the minus 1/2 out, it's going to be x, right? Yeah, so I'm just writing 2x here, then 8x plus 1. Well, if you're not happy with this, you can try multiply this back in to see if it gives you back x to the half. It does, right? If you multiply this into x, it gives you x to the half. So that's just for the first term. And minus, well, because you are taking this out, then it can disappear now. You are left with this first term here. And most of the time, using this strategy is going to make the algebra very simple later. Yeah, so I'm dividing all this by 4x. Now, because seems like we need to combine all the fraction there, but this is just 4 over x hanging around here, so how about we make it 4x as well? So that's going to be minus 16 here as well, divided by 4x, right? Yeah, because it's already got an x there. So just multiplying a 4 and a 4 there. Okay. Okay, so now we simplify the term in the brackets there. So we have this, and then in the brackets there we have 16x squared plus 2x minus 4x squared minus x minus 16 divided by 4x. Note that the x to the minus half is just multiplying the first brackets, right? So I'm just going to write 1 over square root x instead. 16 minus 4 is 12x squared, and that is just plus x there, minus 16 divided by 4x. Now, how do we make it the same as what it wants? Well, do you see that the 16 now has a square root x as well? And the bottom bit also has a square root x. So how about multiplying top and bottom by square root x, right? Yeah? So that's definitely going to make the denominator of the whole thing 4x square root x. And the top bit, well, you got to multiply in, so into the first term, first set, and into the second term. There are just two big terms in the numerator here. Well, but if this multiplies into this, it cancels. So we only get 12x squared plus x and minus 16 root x here. And that is exactly as required. All right, that's it. So part B. The point P shown in the figure 1 is a minimum turning point on C. Show that the x-coordinate of P is a solution to this. All right, so we're going to equate this to 0, right? Because that's a minimum point or a turning point. So we're going to equate this whole thing. Just write them down first. Yeah, it's 4x square root x. Now, because x is greater than 2, so this is not going to give you 0 anyway. We can just multiply that, yeah? And that's going to be, that's going to disappear. So we have 12x squared plus x minus 16 root x equals 0. So how do we make it look like this? Well, we must keep the square root x, and then somehow we're going to take the cube root, right? Cube root, and then I see the cube root here. That's weird. Okay. Okay. So where does the cube root come from? Let me see. Okay. So let me divide the whole thing by 12 first, yeah? Because I see that if I divide by 12, I'm going to get x squared plus x over 12 minus, that is just 4 over 3 root x equals 0. Yeah, because I see the 4 over 3 here. So that is telling me that I should group this term here with this term. All right, so I'm just going to do x squared equals 4 over 3 root x minus x over 12. And so yeah, okay. So if we divide by root x, this is going to become, if you divide by x to the power of a half, the power will get subtracted, right? So 2 minus 1 half is just 1.5, which is 3 halves, right? Yeah? And that will disappear, and that will become, square root x over 12, right? Because x divided by square root x is square root x. Yeah, and I think that's it. So if you power everything by 2/3, Yeah, so that's going to be powered by 2/3 because they're going to cancel there. And this whole thing is just what is required on the right side, isn't it? Yeah, so x equals all that. We just write them down here as required, right? There you go. Okay? That's just it for part B. And now part C. Use the iteration formula that with x1 equals 2 to find part I, the value of x2 to 5 decimal places. Okay, so and then we need to find the x-coordinate of p to 5 decimal places. Yeah, so you see, you got to read the question until the end first, because when you do iteration formula, sometimes you need to keep pressing the calculator, and it does ask you to keep pressing the calculator here because it asks like the proper value of x by just telling you to find the x-coordinate of p. That is just to find the x by using the iteration formula, right? So for I, we're just going to do x2 just once. And again, I'm just going to take this calculator here because that one doesn't work quite well with the iteration. x1 being 2, so 2 equals, and then cancel. And then we have what? Brackets, fraction 4 over 3 minus, okay, fraction, square root, answer, over 12, close bracket, to the power of 2/3. Okay, so that's x2 equals 1.13894 to 5 decimal places, right? I'm just checking. Yep. So that is just done for part I. Part I, we're just going to write x3 equals 1.15693, also 5 decimal places. Yeah. Let me just check again. Yep, I'm happy with that. Another time, x4 is just 1.15649. Another time, x5 is just 1.15651. Doesn't stop there yet. Another time, x6 is just 1.15650. Still converging, still not converging there. Another time, x7, 1.15650 as well. So we can say that it stops at there. So if you try another one again, x8, yeah, it's kind of like completely stopped at the 5th decimal there. Yeah. So part II, we can say that the x-coordinate of p, which is the turning point there by solving the iteration formula, is just 1.15650 to 5 decimal places. Actually, that whole thing is for that, for this whole question, for this whole part. There you go. Okay? So that is just part II done and the whole question done. Okay. Next, question 11. All right. Figure 2 shows a sketch of the graph with equation that the vertex of the graph is at point P, shown in figure 2. Part A, find the coordinates of P. All right, so P we have here. We have a vertex, right, of the V shape. So the vertex happens when you try to make the whole modulus vanishes to 0, right? So that happens at x equals -4, right? Yeah. And when that is 0, you get y as -5. So that means the vertex of P is -4, -5, right? And that makes sense, is in the 3rd quadrant. Part B, solve the equation 3x plus 40 equals 2 modulus x plus 4 minus 5. Okay, as we can see, the 2 times modulus x plus 4 minus 5 is just the V shape we got here in figure 2. And then there is another line here, 3x plus 40, right? So when we want to solve this, maybe it's a good idea to maybe draw the graph roughly to see where that goes. So this is the V shape here and point P being the vertex there. So we already got P earlier to be minus 4, minus 5. So I'm just going to maybe mark there on the scale. And then this line right here, if you look at the gradient part of the line, is 3, which is steeper than the modulus, right? And okay, if we have some idea about the y-intercept of the V shape, if we put 0 in here, right, we're going to get 2 times 4 is 8. 8 minus 5, that's going to be 3, so it's about 3 here. So, actually 40 is, if you look at the linear equation here, there is a 40 here, so that's just the y-intercept for you. Is very higher up. It should be higher than that even, because this is not to scale, guys. So if I draw the line steeper than that one, I mean, we should find out first whether it's like that, steeper, or even like this, So how do we know? Well, let's say we assume like that first, and if we try substitute the x value at point P here to the line, and let's see how that goes. So we do y equals 3 minus 4 plus 40. What are we getting here? This is minus 12 plus 40 is 28. So 28 is like far above point P. So it's like this, right? So 28 is about here maybe, So actually the line is going to look like, this is not realistic, but okay. I mean, you get the idea. So 28 might be, 40 should be higher up, right? So I'm just going to make my line like this, because 40 is not to be there. It's even actually higher up there maybe. So it's going to cut 40 somewhere. Now, just to give you the idea that this line is not going to cut the right wing, because if it were to cut the right wing, this will have to be below the point P. But we have already proved that when you substitute minus 4 into the linear equation, the thing passes this point, which is above point P. So it's going to cut the left wing of the V shape. Well, that logic will tell you what to do with the solving here. Because when you solve, you're going to equate the line to the right part of the V shape. This is the left wing of the V shape, so you're going to put a minus sign into that to modulus x plus 4, so it would become minus 2 modulus x plus 4, sorry, 2 brackets x plus 4 here with the minus. And then you solve this, that's just the best way to do it. So 3x plus 40 equals minus 2x minus 8 minus 5, right? So I get 5x here on the left, and then, sorry, if I move everything to the right part, I get, what is that, minus 57 in it? No, it's minus 53, right? Let me check that. Yep, so x equals minus 53 divided by 5. Okay, so that would just be the answer there. Next, part C. Find the range of possible values of A, writing your answer in set notation. Right, okay, so this one is good and you should pay attention. So I'm just going to do C here, all right? And we should maybe draw, we should think about the graph again, right? Okay, so we have already the V shape here, and it asks you if we were to have the y equals ax here intersecting the V shape at least once, right? So what are we going to have? So if you draw the graph roughly, right, you're going to have that point P there. Okay, and then we know already that this is intersecting at point 3, and that's the origin, and this is minus 5, right? And we have another line, y equals ax. So that line passes the origin. Okay, and we don't know the value of a yet. But we know that it has to intersect at least once. Well, where does it intersect once? Well, here, right? Where it passes origin and point P, because it has to pass origin. So I'm just going to try my best to draw this. There you go. So that's the first case. That's the first case. But as you can see, if we try to ever so slightly tilt the line, like this. Like this. Sorry, no, not that. resize like this. It's going to cut more than once now. But we don't want to tilt like this because it's not going to cut at all, right? So, but if we keep rising the gradient of or increasing the value of A, it's going to cut here. Oh, so there is the range of gradient that it cannot take. Otherwise, it will cut only otherwise it's not going to cut at all. So when it's parallel, of course, it's not going to cut. So when it's parallel, it's not going to cut. But when it's steeper than this parallel gradient, it's going to cut up there, right? So how about we find, this should be a bound, right? The gradient of being parallel to the right wing of the V shape here should be the bound. So let's try that first. So A equals this case where it's parallel to the right wing, yeah? So that's going to be what, 2, right? Because the right wing of the V shape is 2, gradient 2. Okay? Now if we think about rotating this again, so it can be greater than 2. Yeah, it can be greater than 2. And then if it wants to be smaller, it has to be smaller than this, right? Smaller or equal to this. What is this then? Well, we can find the gradient of this. Well, you just take point P here as the point where they intersect. And point P is already what? P is at, what was P again? -4, -5, right? Yeah? So P was -4, -5. That means the gradient here, if the line that passes origin is to intersect that P, then the gradient is just what? Rise over run. So 5/4 right there. So we have another one, 5/4, when they intersect that point P. Well, where do we need to go? Well, we can go smaller than 5/4, right? We can go smaller than 5/4. Keep being smaller than 5/4. Is there any point? We can also even be 0. A can even be 0, right? Yeah. And then can we go negative? Yeah, we can. We can go negative, negative, negative. Yeah, this is a negative line now, negative gradient. Negative until we are at this. Well, we still cut at one point, no matter how negative we are. And then if we are at x equals 0, yeah, we still cut once. And then we are back at this again. So it needs to be greater than or equal, yeah, greater than 2. Can't be 2 because if it was 2, then it would not cut anywhere. That's the 2, right? Or you have to be less than, yeah? So you have to be less than this case, which is 5/4. Right? And that's it. So that is the possible values of A. Now we need to write as set notation. Now they prefer you want to write, you need to write as set notation. So A is a set of, that is just a set already. And then we do A less than 5/4. I'm just going to do like this, yeah? Union, yeah? Or is union. A when A is greater than 2, like that. Yeah, I think that's it. Okay. Well, or you can do a straight line here. Yeah, I think that's more proper. Okay, that's it. That's the answer for part C. Let's look at the next one here, question 12, right? The curve shown in figure 3 has a parametric equations. X equals blah, 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 y equals blah, 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 and you have the curve there. The region R shown shaded in figure 3 is bounded by the curve and the x-axis. Part A, I show that the area R given by that. So parametric integration, guys. So usually the Cartesian or the normal integration is like that, integral to y dx. But the parametric integration is like you change from dx to dt, dx by dt, and then dt. So the point is, because we don't have the Cartesian equation to connect between y and x directly, so that's why we do like indirectly through the third parameter called t, right? So we're going to take this one here. Now y is just in terms of x, and dx by dt is also going to be in terms of x. Sorry, t. Y should be in terms of t, I mean. Yeah. Okay, So it's going to be integral, that's the area R there, integral of y, which is 5 sine 2x, times dx by dt. Well, differentiating 6 sine t is just 6 cos t, right? Okay, and then this is dt. Now looking at the form here that they want, they have all single t, not 2t. I had a 2t here, so I need to change that using a double angle. So that's going to be 2 sine t cos t, yeah, and then 6 cos t here. Now simplifying everything, we multiply all the numbers, we get 5 times 2 times 6, that's 60, I bring outside. And then the square of cos and times sine, right? Like that, as required. Oh, we haven't put in the bound, so not yet. So there is a bound here, upper bound, lower bound, upper limit, lower limit. So this is just area from origin to some point here. How do we get this point? Well, if it happens that you run out of time, or this is like the last minute or something, you just make a guess. That's going to be pi over 2. It's the domain of t there. But if you want to try cy is pi over 2, well, this is at y equals 0, right? This point right here, yeah? At the cursor there. So at y equals 0, that's going to be also 0 for 5 sine 2t, sorry. And if we solve for that, we're going to get another bound for t. So that's just basically sine 2t equals 0. Well, to get sine of some angle being 0, you can have 0 or pi, right? So 2t equals 0 or pi. But the 0 we already have is the 0 for the lower bound. So t is just 0 and pi over 2. And that is why we can say that this whole thing is going to have the limits of 0 to pi over 2. Yeah? That is as required, right? Okay, seems like the next one we gotta integrate that. Hence show by algebraic integration that the area R is exactly 20. Okay guys, this one, by the looks, okay, you need to be able to use the reverse chain rule. Because at least not in this syllabus, not in the GCE UK syllabus, but in the international syllabus. The reverse chain rule is it's like, if you don't know how to use it, in some hard integration question, like you can just check this video in the integration part. Yeah, this video is like the compilation of hardest questions in the kind of like the equivalent math paper here at Edexcel, but international A level. They put out one nasty one for integration, and that's like you have to do this kind of integral twice in biparts as well. So that's like the most brutal integration question ever. But this is easier actually. So hence I'm saying that you should check out this video so that you know how to do what I'm gonna call here the reverse chain rule, right? So the reverse chain rule, right, is that when you see an integral of some function, so the derivative of some function and the function itself is like powered by some number. Yeah. So here you see cos is like fx here, the cos, yeah. N is 2, yeah. So n is to the power of 2, so n is just number 2 here. And if you try differentiate the fx, which is the cos t, you're gonna get sine t. We ignore the 60 for now, yeah. You're gonna get sine t. So this is matching this form. When you see this form, you try using fx to the power of n plus 1 over n plus 1 and with the correction factor k. Alright? Yeah? And I'll tell you a bit about the correction factor in a bit. Okay, so you can see that this is like a reverse power rule. Now, if we just try to get this correction factor k, I'm just going to take the whole thing, right? Just going to take the whole thing, and if you sort of like differentiate the cos, yeah, so if you differentiate the inner part, differentiate the fx there, which is to differentiate the cos t, I'm just going to write cos actually. So d by dt and I have here cos t. I'm going to get a minus sine t, right? Now, but we want so that after differentiating, so that it matches exactly the other part of the integral. So the first part of the integral is the cos squared t, right? Yeah? And the other part of the integral is 60 sine t. So as you can see, after differentiating the inner function of the first part being cos t, it doesn't give you exactly the other part like we intended to do, right? We should get exactly the other part after differentiating the inner part of like the fx here. But we can manipulate, right? So to manipulate, you think how would you multiply minus sign so that it becomes a plus 60 sine t? Well, to do that is just times, right? Times minus 60. But you got to do that on both sides just to show the working. Yeah? So now you get 60 sine t. That means this minus 60 will be your correction factor. Again, just check the video. Yeah? I already attached the video in the link, I think, in the description. So we're going to take the correction factor as k. So this whole thing will be, so the area of R will be just, minus 60. Yeah, just for the k there. Okay. And fx is just cos t to the power of 3 in this case because n was 2. So this is 3. Okay. And divided by what? The n plus 1, which is also 3. And then we sub in the bounds, which is 0 to pi over 2. So that's it. And that will sort of, simplify to minus 20. So when we sub the bound, this will be minus 20 times. Subbing in pi over 2 to cos t, we get, so cos pi over 2 is 0. So that is just 0. Yeah. Minus 20, minus 20, actually. Minus 20 is plus 20, 20 times. Subbing in 0 to cos t, we get 1. So that is just 1. Just it. Okay. So this is in totality 20. And that is exactly what we want to show because it says 20, right? So if you didn't know reverse chain rule, or if you didn't know how to use this, you would have had to do the substitution, I think. So you sub cos t equals u. That would have also been fine, but there's some more steps. And I'm saying again that in some root or integration question in the IALP4 compilation, they required you to do this like twice in the same question, in the same integral even. Yeah, that's brutal. You can go check that out in the video. Yeah, the syllabi are also quite similar between the international and the UK one, so don't worry. All right, so we have done part 2. So part 3. Okay, now we have figure 4 instead. Part of the curve is used to model the profile of a small dam, shown shaded in figure 4. Use the model, and given that x and y are in meters, right? The vertical wall of the dam is 4.2 meters high. There is a horizontal walkway of the width mn along the top of the dam. Calculate the width of the walkway. Okay. So we're just going to calculate the walkway mn here. Yeah? Right. So, well, as you can see, the line mn is probably part of a straight line cutting the curve on the same level as mn. That means the height here being the y coordinate of these 2 points. So we're just going to put y as being 4.2 actually to the function, and the function was just either these, one of these. So we're going to say y equals 4.2, so we're going to sub it in here to get the t value, and then after we get the t value, we're going to plug in here to get the x values for 2 points, right? So y equals 4.2, so 4.2 equals 5 sine 2t. Okay? Yeah, so is it exact? We don't need to go exact, right? Okay, so sine 2t is just, so that's 4.2, yeah, Yeah, 4.2 over 5. So how many t values do we need? Yeah, I think we need 2, right? So that point and that point. We're going to get the first 2 smallest values there. Okay. So it's just going to be the first quadrant and the second quadrant where sign is positive, right? So let me get another one. Okay. So we do arcsine. This is in radians. Okay, I'm already in radians here. Arcsine of 4.2 over 5. Yeah. So 2t is just, that's the smallest angle there in the first quadrant. And if I do, pi minus that, it's going to give me another one in the second quadrant, right? Okay. So t is just going to be, well, I'm just going to do the first one divide by 2 first. So I'm going to get 0.498642. And then the other one, pi minus that, and in brackets, divide by 2. So 1.072155. Okay. So those are the 2 t values there. If I plug that into the x, I'm going to get the answer there. So just, I'm going to plug that in first. So store and then equal. What was it? 6 sine t. So 6 sine answer. That's going to be 5.2693 blah blah blah. And then the other one will be 6 times sine of 0.498642. Yeah. Okay. And then we're just going to round this to, oh yeah, no, we're going to have to subtract them because those are the 2 x values at m and n. So mn will be equal to 5.2693 blah 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 minus 2.8694. Ooh, okay. So I'm just going to do 3 decimal places maybe. So this is going to minus 5.2693. Yeah, so that's going to give me 2.399 blah blah blah. So 2.40 maybe. Yeah, I'm going to have that. Okay, so 2.40 is my answer then. Okay, so that's not too bad, right? Question 13, the function g is defined by that, where k is a constant. Deduce the value of k. Okay, so k is the value that x cannot be. Well, yeah, this might be tricky, but I mean, how do you know, right? But maybe if you forget, you should know that the denominator, right, cannot be 0. So in part A, we can just say that ln x minus 2 cannot be 0, right? It cannot be 0, yeah? So that means ln x cannot be 2, so that means x cannot be e to the power of 2. Yeah, we just solve it as if it were an equation, but then x cannot be e to the 2. Because if you plug e to the 2 in the x, you're going to get 0 there. Okay, so that's part. So k is just e to the 2. Part B. Prove that the derivative of g is greater than 0. Okay, this might be tricky. I picked this because I saw this part. Alright, so we need to do the derivative there. So g dash x is just doing differentiation for the gx. So this is probably quotient rule is the best one. So v du. So differentiating the top bit, we get, the first term we get 3 over x, and the second term disappears. Okay? Okay, that's v du. So u dv, so u ln 3 ln x minus 7. dv is differentiating the bottom bit, we get 1 over x, right? That's just ln x. Divided by the bottom bit squared. That's it. And now we need to prove that this is greater than 0 somehow. All right. So let's have a look. If we pull 1 over x out, right? If we pull 1 over x out, what do we have? So I have 1 over x here, big bracket maybe. So 3 ln x minus 6, expanding all out, right? Minus 3 ln x as well, plus 7. There you go. And the bottom bit here is a square number. So no matter what x is, as long as it's not the k, then we are fine. So inside the brackets, the minus 3 ln x disappears there. And we have left with, so it's 1 over, right? So 7 minus 6 is 1. So this is 1 over x ln x minus 2 squared. Now, well, how do we prove that this is always greater than 0, right? For all values in the domain. Well, because ln x minus 2 squared is always greater than or equal 0. All right? And ln x minus 2 is not 0. It's not 0, so it can only be that. It cannot be 0 because it was the denominator part, remember? So if I wrote this, it would be wrong. It's not 0 anyway. Yeah, it's not 0 because it cannot be 0 down here, so we can't write that. So this is already greater than 0. And x is also greater than 0. So they are two positive numbers. That's why it's got to be greater than 0. Yeah, so two positive numbers multiply to a positive number. Yeah, or you can just write, therefore, 1 over x ln x minus 2 squared must always be greater than 0. Well, that means g dash x, always greater than 0 for all x in domain of G as required. Yeah, we have proved it. Part C. Find the range of values of A for which G of A greater than 0. Okay, G of A greater than 0. Okay. So we're gonna put 3 ln x here. I'm just gonna put x first. Divided by ln x minus 2 greater than 0. All right, we're gonna solve for that. Now, well, we don't know if this is a positive or a negative, right? So we can't really move it to the other side. That's going to be risky. But what we can do is solve this as if they were like an inequality here, right? So I'm just going to try put the two parts to 0. Well, that can be 0, right? But if I try put it to 0, we're going to get the critical value. So this is ln x equals 7 over 3. So x equals e to the 7 over 3. And that is just, again, we got this already. So x is e to the 2, right? Yeah. Was it? Yeah. Now, these are two critical values. Okay? Now, let's think a bit about it. If we put this in a number line, yeah? So e to the 2 is greater than, no, it's less than. So e to the 2 is here and e to the 7 over 2 is here. Okay. Now there are three ranges, like 3 sections of x values that we can consider. Let's talk about when x is less than e to the 2. Of course, it has to be greater than 0, so I put 0 here. So let's consider, it can't be less than 0, right? So we're going to consider from 0, well, it can't be 0, yeah, from 0 to e to the 2. What happens here? If we consider this range here, this will be negative, right? Yeah? Because if you put, okay, if you put e to the 2, which we can't put that, but if you do put e to the 2, this is going to be 0. So if you put something greater than e to the 2, for example, e to the 2.1, it's going to be a positive number, right? This whole thing. Okay? But what if you put less? Well, if you put less, right? If you put less, this is going to be a negative. Okay? What about this? If you put this less than e to the, like, okay, so if you consider the critical value of the top bit here, which is e to the 7 over 3, if you go less than that, you're going to get a negative. You're going to get a negative for this. So that means if you go less than e to the 2, you're going to get a negative for this and a negative for this, right? So that works because we want, if we have both to be negative, then they divide to a positive number. So this works. And usually if this range works, then the next one might not. Because this one, yeah, you're going to get this to be positive now. And because it's still less than e to the 7 over 3, this will still be a negative. So that doesn't work because we want greater than 0 here. Yeah, that doesn't work. And this one here, greater than that, it will work. And we can't get 0 here, so this cannot be e to the 7 over 3, because if it was, then this will vanish to 0. So we got to go greater and cannot take 0, greater than e to the 7 over 3. But it can go forever, because if x is greater than e to the 7 over 3, this will be positive, and that will also be positive. So that works, all of them, yeah, go to infinity. So the answer to x is then x, okay, so x in the range of e to the 2 and 0, or x greater than e to the 7 over 3. That would just be it. So I think this whole question is quite good for B and C. I think they should be hard. All right. Okay, so that's it for this one. Number 16, use algebra to prove that the square of any natural number is either a multiple of 3 or one more than a multiple of 3. All right, so, well, you need to know first that a natural number is just a positive integer, right? And because this is something to do with showing whether a square of that natural number is a multiple of 3 or not, right? So I know that you can do like odd or even, but if you try do that, it's not going to work, because you can't really prove whether it's a multiple of 3 or not a multiple of 3. So we're going to do this. We're going to put n, yeah, is a natural number. I'm going to say that n is a natural number first. So this is question 16. Natural number. And then it can be split into 3 cases. So n is 3k, a multiple of 3. N is 3k plus 1, one more than a multiple of 3. And you have another case where it's 3k plus 2, 2 more than a multiple of 3. And if you keep going, it's going to repeat in the loop. Because if you do 3k plus 3, that is actually coming back to being a multiple of 3. So we're not going to do that. These are just all there is. So this is already exhausted. So if you, yeah, so if you think about what if you put it for odd and even, right? If you did odd and even, then that would have been n equals 2k and n equals 2k plus 1. But because I'm doing a multiple of 3 here, so there are 3 cases. If you want to do in terms of multiple of 4, there are 4 cases, and so on, yeah? So for each one, we're going to do the same thing. We're going to square the n. So n squared equals 9k squared here. And this one is indeed a multiple of 3 because we can factor 3 out. So a multiple of 3, right? What about the other one? So this one in 2 is just 3k plus 1 squared. So that is just 9k squared plus 6k plus 1. Well, we can factor out 3, right? So 3, but then the 1 here will remain outside. So we have 3k squared plus 2k here, yeah? Plus 1. This is 1 more than a multiple of 3, right? So that's the second case. And the third case here, we do the same thing. We square that. And then we have 9k squared plus 2 times 2 times 3 is 12k plus 4. Well, for this one, it needs a little algebraic manipulation there if you split 4 into 3 and 1, right? So you're going to have, I'm going to do this first so that you follow. Split them into 3 and 1. And then here we have 3 times 3k squared plus 4k plus 1, and then another 1 outside. Yeah? You can just try check that if you're not happy. So this is also 1 more than a multiple of 3. So you see, these are all the cases possible for a natural number in terms of being a multiple of 3 or not. So any natural number is either a multiple of 3 or 1 more than a multiple of 3, because we already shown that one of the cases being a multiple of 3, the other two are 1 more than a multiple of 3, right? We already showed that. So we're done. This is as required. Yeah, that's it for this whole question, right? Okay, let's go to the next year, October 2022 now. Sorry, this is October 2021. Okay, number 8. The curve C has equation that where P and Q are constants. Show that dy by dx is that. Well, this is probably not too bad for part A, but for part B, there's something more than this. Okay, so we're going to differentiate implicitly first here because all the terms are like, you know, mixed together like that. So we're going to implicitly differentiate this. So differentiating p x to the power of 3, we bring 3 down. So we get 3p x to the power of 2. Yeah, this is part A, sorry. And then plus, don't forget the product rule here. So u dv, so u is qx, dv is dy by dx because it's just a y. So differentiating y respect to x is just dy by dx. So this is u dv and v du. So du is differentiating qx, so we get a q. And du, v du, yeah, so v is the y. Okay, that should be it. And the next part is differentiating 3y squared. So that's going to be 6y and a chain rule dy by dx, right? I hope all of you guys know what I'm doing here. And then differentiating the right part is just 0, right? So that's a constant. And then we rearrange this to get dy by dx. So if you look at these two terms, so we're just going to add them. Qx plus 6y dy by dx. And the other terms will be moved to the other side. So it's a minus, what should I get? Yeah, 3px squared minus qy, like that. Okay, or divided by qx plus 6y, yeah? Well, actually, I'm already doing dy by dx here. Okay, so I think a, b, and c are integers, so let's check. Yeah, a is minus 3, b is 1, b is minus 1, q is q here, c is 6. So just going to write a is minus 3, b is minus 1, and c is 6. There you go. Part B. Given that the point P minus 1 minus 4 lies on C, the normal to C at P has that equation. B, find the value of P and the value of Q. All right. So it gives you the point P which lies on C. C has this equation here, guys. So we can already substitute that into the curve equation to see, you know, what we have there. So just P substituted minus 1 into the x there, and Q minus 1 times y minus 4, and then plus 3y squared equals 26. Yeah. So minus 1 to the 3 is just minus p there, and that would be 4q, and that would be minus 4 to the 2 is 16, so that is 48. Yeah, equals 26. Well, rearranging that, we get minus p plus 4q equals what? Minus 22, right? Yeah? Just moving to the other side. So we're going to keep this as equation 1 because I think p and q here seems like we need to solve it simultaneously. Yeah? And the other information we have here is that the normal to c at p, we already got the p there. The normal to c at p has the linear equation of that. Okay, so you got to get the gradient from that linear equation. And the simplest way to do it is maybe to make y the subject if you don't have the formula in mind, but you can do minus a over b there. But I mean, if you rearrange, you're going to get the same thing. So if you make y the subject, you're going to get minus 19x minus 123, yeah, over 26 here and over 26 here. So that is saying that this normal line, mn here, is equal to, the gradient of the normal line is just minus 19 over 26. Would that mean the tangent, right? The gradient of the tangent would be flipping the fraction and putting the minus sign in. We get that. And this must be equal to the derivative when substituted minus 1 minus 4 into the dy by dx, right? So that would be equal to, subbing in, we can use this expression here. Surely it should be right. So minus 3p x squared, x is minus 1. Yeah, we are using the minus 1 minus 4 point there. Minus q y is minus 4, all divided by qx plus 6y, like that. Okay, so we're gonna just tidy up and get this equation. We're gonna solve simultaneously with the first equation I have there. So seems like here we have what? Okay, I'm just gonna multiply this whole thing to 26 while also simplifying it. So this is minus q minus 24, right? And the other one is just cross multiplying there, 19 brackets. So what is this? This is 1 times minus 3p, so that's minus 3p. And the other one is also plus 4q. Okay? So what's that? That's minus 26q. What is 26 times 24? Sorry, it's 24 there. 624. So that's q and minus 624, was it? Yep. Yeah, equals 19 times 3 is just 57. So that's minus 57p plus 19 times 4 is 76q. Okay, so let's have a look. We have, if we combine all the terms there, right? Moving everything to the same side, we get 57p here on the left side. And then I'm moving 76q to the left side as well. I get 102, isn't it? That's 102, yeah. 102q and then equals 624. That's my second equation there. All right, so we're gonna use that. Now, if we check this, right? Well, I'm gonna maybe eliminate the p term, yeah? So I'm gonna do here, if I multiply that first equation by 57, I'm gonna get minus 57p here, and plus, and 57 times 4, yeah, I'm gonna get 228q here. And on the right side, I get what was it again? 57. Okay, that's a big number there. Okay, minus 1254. That's the other equation, say equation 3. Now I'm gonna subtract them. No, actually add them. Yeah, if we add them, p goes away. So we have what? 126q here equals, what is that? Okay, let's say this is a minus here actually. Yeah, and then plus 624. Ooh, okay. So q is going to be answer divided by 126. Wow, that's nice. Minus 5. So q is minus 5. That means p is, where can we get p? Okay, I'm going to use this first equation here to get p. So p is just going to be 4q plus 22, right? Yep. wait, hang on. Yep. So that's just 4 times minus 5 plus 22. That is going to be 2. Yeah? So that's the answer there, P and Q, guys. All right? Okay. Let's do the next one. Number 11. Figure 4 shows a sketch of the graph with equation this. Another modulus function again, where k is a positive constant. A sketched the graph with equation y equals fx, where fx is all that. So it's just the modulus, but flip and then shifted up by k, right? So we're gonna sketch the two together. So I'm just gonna do like this one first here, and maybe for simplicity's sake, just gonna duplicate that and then do this, right? Because there should be like a flip, and so if you flip it, it's gonna be this first, and then you move up by k, where k is a positive constant. So there you go. So this should be k here. If we put that to 0, that's going to be 3k. So that should be below, a little below here. There you go. So this is 3k, right? If you put x to 0 here, this is going to be 3k. And this is going to be k here around. Okay? And coordinates of minimum point, maximum point. Okay, so this one is maximum point being the vertex is at x equals minus. So this is, so if we want the vertex of this at the beginning, yeah, we put 2x minus 3k equals 0 to get the vertex. 3 over 2k, right? Yeah, that means this is 3 over 2k, comma, the maximum being k because that's moved up by k. The coordinates of any point where the graph cuts the coordinate axes, we sketch the graph y equals fx, yeah, that is just the thing there. And then this is fx. So we need to find these 2 points as well, yeah, there. And that happens when y equals 0, okay? So put y equals 0 here. 0 equals k minus absolute 2x minus 3k, yeah? And then we're going to solve for that, right? So just solving for 2x minus 3k equals k, and minus 2x plus 3k equals k, right? Yeah. So for the first bit, we get x equals 2k, and for the second case, we have x equals 1k, or 1, or k, yeah? So it's just 2k here and 1k there. All right, so I think I've done everything there. Part B. Find in terms of k the set of values of x for which that. So this is the same inverted V shape, but another line here, x minus k. So x minus k, well, it seems like the x minus k here is less steep. So less steep, I'm just going to cancel out this one, yeah, less steep, and it intersects at minus k. So minus k is probably around here, and then less steep go like that, maybe, okay? So we want to find where the V shape is above the line, right? So V shape above the line is just from this range to this range. So it's this part here, yeah, this part. So we want to find that intersection and that intersection, and the x values will be in between those two, right? So in this case, we do separate. So we do k minus 2x minus 3k equal x minus k first. Yeah, so that's going to give me, so k minus 2x plus 3k equals x minus k. So x equals, so that's 4k and 5k, so 5 over 3k, right? Yeah. Okay. And the other case is k plus 2x minus 3k equals x minus k, right? So moving everything, I get x on the left and then k on the right. So that is just, yeah, okay, solved. So put this into the range, it should be in between. So it's just that. Yeah, where the graph is, the V shape is above the line. All right. Now let's have a look at part C, right? So find in terms of K the coordinates of the minimum point of the graph with equation that. Okay. So we just need to know for this one, yeah, part C here, that it's just a transformation. Okay. So f of x, what was f of x? Well, f of x was just this inverted V shape. Okay, where the minimum, because the point we care about here is the minimum. So why does it say minimum there, where actually this was in fact a maximum? Well, because you have a minus here, yeah? So you have a -5 here, that is like flipping the thing in the x-axis while also enlarging the thing as well 5 times, right? Enlarging on the y-axis, stretching. So it's going to look like an inverted, like it's going to be a normal V shape, right? So we just take the minimum, sorry, the maximum there, it was 3/2k, comma k. So that was the previous maximum. So what do we do with this, right? So we're going to do the y first maybe. So the y will be multiplied by -5. Yeah, so you get -5k. Because we have a -5 here. And then you're going to add 3 as well. So that is +3, yeah? So this is +3, and this will become -5 plus 3. Well, what happens to the x? Well, the x, we have a 1/2 here, so that's just going to multiply the thing by 2. So the x here will just be multiplied by 2, and that's it. So just 3k. And that will be the maximum. Yeah, so that would be the answer to this question. That's it, not that hard, because if you know transformation, that's going to help. Yeah, that's the minimum there. All right, next question, number 14. Okay, so what do we have here? Water flows at a constant rate into a large tank. That's a large tank there. The tank is cuboid with all sides of negligible thickness. Okay. The base of the tank measures 8 meters by 3 meters, and the height of the tank is 5 meters. Okay, we got everything in the diagram there. There is a tap at a point T. Okay, and at the bottom of the tank as shown. At time T minutes after the tap has been opened, the depth of water in the tank is H meters. Okay, there you go. Water is flowing into the tank at a constant rate. Well, we're going to note this down. So this is volume rate, dV by dt then. Water is modeled as leaving the tank through the tap at the rate of that. So you see that there is a water flowing in and also water going out, like a leak. Okay? So I picked this one because there are 2 rates in the same question, if you like. Okay, so let's do this. This is question, what was it again, 14. So we need to show that according to the model, blah, blah, blah. So that's basically dH by dt. Now, but we are given the information only about the volume flowing in and out, right? So the inflow volume there is, so dV by dt. But when we write dV by dt is the net volume flow rate. So the in minus the out maybe. So I'm just going to write that is going to be dV by dt in minus dV by dt out. It's like when you're doing like a net income sort of thing. You got to do earning minus expenses if you like. So that is just also the case here. So we want to find the net volume flow rate, right? Okay, so let's compute this. So dV by dt in, we have a net flowing in of 0.48 meters per minute. We're going to keep things in meters per minute here then, I think. Okay, water is modeled as leaving the tank. So that is minus 0.1 h as well. That is dV by dt. Okay, we're not done. This is just dV by dt. But in the relation here, it is just h and t. So, and this is important. How do you go from v dv by dt to dh by dt? Well, here's the key step. You got to get what's called the chain rule equation. So you have a v, an h, and a t. Well, the only way it makes sense is maybe to do, okay, because dh by dt is the thing you want, so you make that the subject. And then you do dh by the other, by d, the other variable that you want to put it in, which is the volume here. And then multiply by dv over dt, because don't forget we need the t still. This is all about rates. Okay? So that means, well, we have dv by dt already, which is this whole guy. But we don't have the dh by dv yet. Well, we need to work on that, right? So dh by dv can be found by you having to find the volume formula in terms of h first. Well, how do we do that? If we look at the geometry here, you can see that the volume of the water changes according to the height or the depth, if you like. So, but the cross-sectional area is kept the same as 8 times 3. So volume in terms of height is then 24h, don't you think? Because the height can change according to where the surface is, but the cross-sectional area doesn't change, right? So there you go. That's volume as a function of h. Well, that means if you want to do dv by dh, then it's going to be 24. So if you want dh by dv, then it's going to be 1 over 24, right? Now we can plug 24 in there, so dh by dt is just 1 over 24 times dv by dt, which is just the thing we got earlier, 0.48 minus 0.1h, right? And if we simplify that, we should get according to what they want there. So let's see. Okay, so if I multiply the whole thing by 1200, yeah, because that's what they want there, 1200 on the left side, multiplied with dh by dt. So 24 dividing into 1200, we get 50, right? 50, yeah. So that's 50 times this whole guy. And then we get the last line, 1200 dh by dt. 50 multiplying into 48, I believe we should get 24. Yep. 24 minus 5h as required. Yeah, so if you didn't know that the rates can also add up, and we call it a net rate maybe, probably A would have been hard. Okay, so now let's do B. Given that when the tap was opened, the depth of water in the tank was 2 meters. So that is like the initial h then, yeah? And then we want to solve for the differential equation here. So when you see the rates here, usually it is just separation of variables, integration technique, yeah? So I'm just going to maybe do like dh and then move the whole 24 minus 5h here and equals 1 over 1200 dt up here. Just moving things around and put the integral sign, yeah? We're going to integrate 2 sides. Okay? So integrating the left-hand side, you should get a natural log of then 24 minus 5h. But then don't forget to do the reverse chain rule. So we get minus 1 over 5 as well here. It's just dividing by minus 5, which is the same thing there. And this is, we get t over 1200, yeah? Okay, just checking here. Okay, everything's fine. Okay, so, oh, I forgot the plus c. Now the plus c can be found, right, by just using what's called the initial condition there, where when the tap was open, which is at t equals 0, because that's the start. So at t equals 0, we're going to plug in the height of the tank being 2. So t equals 0, height equals 2. And then I'm going to plug it in, minus 1 over 5, ln. So height equals 2, so that's going to be 24 minus 10. So we get ln 14 here. And that's going to be 0. And we get the value of c then. So that is just the value of c. Yeah? Okay? And we can keep it like that, you know, there's no worries there. and then we want to put everything back into the expression to make h the subject of the equation here. So I'm gonna go down a little bit, and then so we get 1 minus 1 over 5 ln 24 minus 5h. Yeah, well, because the height cannot be greater than 2 anyway, so we can take the absolute out. That's no worries. Okay, and then equals t over 1200 plus c, which is that. Yeah, okay. Now let's rearrange this. So if I move the c to the left, I get 1 over 5 outside everything, and inside I have ln of 14 minus ln 24 minus 5h. Yeah, equals t over 1200. All right. And then, yeah, if you multiply by 5 on both sides and simplify the log term here, you have ln 14 over 24 minus 5h using a log property there. Yeah, merging the log terms. And then we have 5 multiplying to the other side. I have t over, what's that, 240. Yeah. Okay, we're getting there, right? Yeah, k is constant to be found. Okay, that's a little complicated there. Anyway. Yep, I'm fine with that. So now we want to make h the subject. So 14 over 24 minus 5h equals e to the t over 240. Yeah. Okay, and then we just solve for h, right? So 14 equals 24 e to the t over 240 minus 5. Well, that let me just do this again. So I'm just going to do 14 over e to the t over 240 equals 24 minus 5h. Yeah, like that is better. Now we make 5h the subject. We get 24 minus 14. Now e, I'm going to pull it up here and putting the power as a negative like that. And then I have it there. h equals 24 over 5 minus 14 over 5 as well. E to the power of minus t over 240. Okay. Yeah. Let me double check everything, right? Because you can't be so careless there. Okay, I'm just going to check if I got anything wrong. So, okay, yeah, I think that's fine. I think mostly it's fine. Yeah, should be that. Okay, so part C. Given that the tab remains open, determine according to the model whether the tank will ever become full, giving a reason for your answer. Okay, so to become full, right, h should reach 5 meters. Okay? Now, does it reach 5? Well, we'll see. So if you do t tends to infinity again, yeah, classic, right? Because here we want to see if you leave it for a very long time, what happens to it, yeah? So the e to the minus t over 240 will reach 0. So that means h maximum, h will reach 24 over 5, right? Because this whole thing will become 0. And what is that? That is just 4.8 meters, right? And that is not quite the height of the tank here, okay? So the water level is only approaching 4.8 meters. Yeah, meters from the bottom, right? So the answer is no, it will. No, it will not. Okay? No, it won't become full. All right, so that's it. Next, question 15, yeah? Part A, express that in a harmonic form. Alright, so let's just expand the r cos and r sin. So this one is interesting because of the later questions here, later subparts here, as you can see, yeah? And I think this is very interesting one. This is a big wheel, maybe a London Eye or something, yeah? No, a water wheel. Alright. So if we expand the harmonic form, r cos theta plus alpha, we have what? We have r cos theta cos alpha, yeah? And then minus r sine theta sine alpha, yeah? And if you map this to the original function there, you have 2 cos theta minus 1 sine theta. So that means the r cos alpha, right, which is the remaining term here, must be equal to 2 because you already compare cos theta to cos theta, so the remaining is r cos alpha should be 2. So I'm just going to write that. Okay, and r sine alpha should be just 1. So that means r is just square root of 2 squared plus 1 squared, that is just square root of 5, right? That's the r there. And then, well, you can find alpha from either one of them. So I'm just going to take the cos here. Alpha equals r cos, yeah, 2 over r, which is that. Okay, that's just alpha. And we need to give the value into 3 decimal places. So that's in radians. So I'm just going to do radian here. That's already in radian. And then r cos 2 over root 5, right? So that's it right now. Yeah, that's 0.463647609, and then equals 0.464, yeah, 3dp. Okay, so we already got the form, so I'm just going to write again. It's just root 5 cos theta plus 0.464. That's the final answer there for part A, right? Part B. Oh, this is long. Okay. Part B, it asks the maximum height of P above the water level. Okay, so maximum height of P, point P here above the water level. So we imagine the highest point it can go up is that point. Yeah? So that's just the maximum value of H, basically. Now, if we look at the function H here, right? Okay, this is already partially harmonic from the original form here. So if we match up, right, we're going to see that the 2 cos theta here will become a 4 cos something else. Okay, so it's like you are changing from root 5 cos theta plus alpha here to 2 times, right? So we're going to have 2 times root 5 cos. And then the theta, rather than being theta, we actually have 0.5t. Okay? All right? And then plus the same alpha. The alpha doesn't change here when we sort of like apply the form to the problem like this. Yeah? That is just the harmonic part. And we also have the 3 plussing here. Okay? So that's just the modeling equation there for the H here, yeah? We just got it. Now we're going to use it. So the maximum height of P above the water level would just be the maximum value of all this guy, right? So how do we get the maximum there? Well, H max, right, this is for part I, will just be when this whole thing is 1, right? Because that's the maximum value that cos can get you. So that's just 3 plus 2 root 5, basically. That's it, because that thing becomes 1. Okay? And then part II, the value of t when this maximum height first occurs, giving your answer to 1 decimal place. So I just made this 1. That means to find the time when this maximum occurs, you just need to take that equating to 1 and solve. You don't need to take the whole equation, right? Although you already know that the maximum height is 3 plus 2 root 5, then you don't need to take the whole thing. You just take what you made for cos earlier and put it to 1. Like that. Okay? So we just want the smallest value. Now, time, there is no domain here. So time is going to start from 0, right? That's how time starts, right? The beginning of everything, yeah? So the range of time is 0, right? Greater than 0, I mean, right? So that means 0.5t plus 0.464 must be greater than, you know, you multiply the 0 by 0.5 and then plussing it by 0.464, you should get greater than 0.464 no matter what. So we are getting some idea about the range of angles that we should expect when solving the angle from the cos function there. So now, I'm just going to find the principal angle first. Well, actually, you don't need to because cos of 0 can only give you 1. Yeah? But if you put this whole thing as 0, right? Let's say you put 0.5t plus alpha equals 0 because arc cos 1 is 0, right? You're going to get a negative value of time, which is not what we want, right? So the time that it first occurs here will be the smallest positive value of t. So we're going to equate this, yeah, which is the angle for cos at which it has cos of some angle is 1 here. It's going to be, you know, you have 0 at first when it's 0. Sorry, you have cos 0 equal 1, right? And then if you go another round, you get 2 pi, don't you? So that's the smallest one. So t will then be equal to 2 pi minus 0.464 divided by 0.5, basically. Okay, so, but I'm actually going to use a more precise number there, which is this guy right here. So answer. So we get fraction 2 pi minus answer divided by 0.5, right? Yeah. So that's just 11.3 significant figures. Yeah, 11 point. I'm just going to write everything first again, guys. 11.6, right? And this is in minutes, right? No, it's in seconds, right? Isn't it? The time in seconds, yeah. Yeah. Okay, so that's just it. And then part C, right? A single revolution of the wheel, P is below the water level for a total of t seconds. The water level is here, yeah? According to the model, find the value of t, yeah, giving your answer to 3 significant figures. You have to be able to visualize this first. That it's like, okay, P will somehow, I don't know which way it rotates, but okay, let's say clockwise, so P is going to go down here, yeah, you just follow the cursor there. And then below the water level, it's going to be underwater, right? And we need to find how long it takes to be underwater. So from here and then underwater, until it goes up, back up here and out. So the duration of time in the water, under the water, we are finding it as the big T here. All right. So we need to know this water level first, right? So let's see. So we haven't quite read. I haven't quite read the question yet. It's free. The point P is at the end of the pedals. Okay, the water level is assumed to be horizontal of a constant height. Okay. And P is about the vertical height 8 meters about the Oh, this is the height h meter above the water level is modeled by this equation. So height here is not measured from the ground or anything. It is measured from the water level, I just realized. So that means when you reach the water level, you got to put the whole thing here, to 0. Okay, so we're going to put the whole thing there to 0. So h equals 0 here equals 3 plus, and the harmonic form we got earlier, 2 root 5 cos 0.5t plus 0.464. And we're going to solve for this, right? So, well, yeah, need to solve for that. So we just have minus 3 over 2 root 5 equals cos of 0.5t plus 0.464. And we are solving for this. Now again, let's consider the range again, which is going to be the same because the thing inside the cos function there doesn't change. So this is again 0.5t plus 0.464 greater than 0.464. Just to get some idea again. Now, let's find the principal angle first. I'm just going to find what's called a beta. It doesn't have to be beta because we already used alpha, right? So beta is just a principal angle at cos. I'm going to do a positive of the other side there when we do at cos, because I want to get some idea about the principal angle. And because we bear in mind that the cos value here is negative, so the cast diagram will go like cos negative is only happening at this and this. Yeah, it's quadrant 2 and quadrant 3. Yeah, cos being negative. But the beta here is just this guy and this guy. All right. So how do we get the answers? Well, you got to sweep from the positive x-axis. This is your first answer. I mean, if it's in the range, of course. And this is your second answer. And if you want a third answer, you need to keep going. You need to keep sweeping like that. Okay, so let's get the answers here. So for the first one, we're going to have, so we're going to put the at cos 3 over 2 root 5 later. But I'm just going to write here first that 0.5t plus 0.464 equals pi minus beta. Just have a plan first, and then I'll just do everything at once. Or, what do we have else? What else do we have? Pi plus, right? Okay, now, well, I think for a single revolution, we can just rely on these two. We don't need to find other roots as long as these two are in the range, right? So are they in the range? So let's find out. They should be, right? So because pi is already 3.14 and beta should be less than pi over 2. So there you go. I'm going to get beta first. So I'm going to do at cos 3 over 2 root 5. That's my beta there. Okay? Yeah? So I'm just going to put away my cast diagram here. To be here maybe. And then I'm writing beta here is 0.835482. Stopping there. So this is going to be that. That means if we want to find t, right, it's going to be, as you can see, there is just a minus beta and a plus beta there. So it's just pi plus or minus beta divided by minus 0.4, wait. Yeah, sorry, 0.464 divided by 0.5. Okay? So we're just going to do pi like this, plus first then. Oh, let me put that whole thing in brackets. Yeah, pi plus that beta minus 0.464 and then all over 0.5. Oops. Yep, so it's going to be 7.026149 first. Or the other one, now we can change that to minus, right? Or 3.684222, yeah? So if we minus this answer, by 7.026149, we're going to get the change in time. So t is just going to be equal to 7.026 blah 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 minus 3.684 blah blah blah, and that is going to be equal to 3.341, and we want three significant figures, so 3.34 would be the answer for seconds. Yeah, okay, that's it. Alright, so in reality, the water level may not be of constant height. Explain how the equation of the model should be refined to take this into account. Okay, so the water level may not be of a constant height, right? So I think when we consider that the model should be refined, so if we look at the equation here, for h equals 3, and in fact it's just 3 plus 2 root 5 and cos everything. So the cos part is the nature of how the wheel turns, right? And that shouldn't change, because you know the machine that turns the wheel has a constant angular speed, probably, physically speaking. So the cos function here comes from that. And 2 root 5 is just probably like the length of the distance of P away from the center C. That's the 2 root 5 there, probably, or something related to that. Now, when the water level can vary, right? Because it says here, in reality, the water level may not be the same height. So that means the only part that we can sort of like crack on here to make it more realistic is the plus 3 here. Right? Because again, you can't change the periodic function, which is the sinusoidal part, which is the cos here, because this is the nature of the wheel turning. But 3 comes from kind of like nowhere. Maybe it's according to the water level at first. So that means if the water level can vary, then this part should be able to vary according to the water level. So let's say the water level is rising up by 1, then this should change by 1. Okay, so maybe 1 less, because when the water level rises up by 1 meter, h is going to be, smaller by 1 meter, right? So I'm just going to write here for part D that the constant 3 should change as, just going to keep writing down here, as when should change because when water level changes, the height h here can get smaller or larger. Yeah, that's just some context there for you guys to understand. All right, and that is just it for this whole question. Now let's have a look at the next year, June 2022 now. Okay, we are closing in, guys. Okay, the first one, and this one is the one I was talking about earlier. So June 2022, was it? Yeah, June 2022, question 5, the first one. The table below shows corresponding values of x and y for y equals log base 3 of 2x, and then the table using part A using trapezium method or rule with all the values of y in the tables, find an estimate for that. Okay, so using trapezium, right? So it's just again the area under the graph, or we can just write that whole integral there, no worries. It's going to be about, right, 1 over 2 times the width of each strip, which is 1.5 there, times, yeah, again guys, the first one plus the last one, and then plus, I never got enough space for this, right? 2 times all the other ones added up. So 2 plus 2.26 plus 2.46, bracket, bracket, yeah? Just checking everything. Okay, so let's find that. 1/2 times 1.5 times, open bracket, the first one 1.63 plus the last one 2.63 plus 2 times there, you got to be careful. 2 plus 2.26, is it? Yeah. Oh, hang on. Plus 2.46, yeah. 2.26, 2.46. Close. Okay, so that is just 13.275. Okay, and we need, how many sig figs do we need? I'm just gonna, oh, well, 2 decimal places, right? So I'm just gonna give it that actually. I'm not gonna round because it doesn't say, so I'm gonna go with that. Okay. Now, that's part A done. Part B. Using your answer to A and making your method clear, estimate those 2 parts. The integral of the same bounds, you see? Same bounds, same upper and lower limit. But then we have log base 3 of 2x to the power of 10. Well, using log property is just 10 times, right? This is just 10 times log base 2x, log base 3 of 2x. So that is just 10 times because you can take 10 outside the integral like that, yeah? So 10 times just all that, because what is left in the integral is just exactly the same as this that you use trapezium rule to estimate, okay? So that would be 132.75 for the first one. Part II, this one is a little trickier, yeah? So you need to manipulate the integrand first, the thing inside the integral. So how do we do it? Well, how about log base 3 of 18 can be split into log base 3 of 9 times 2x, right? Because I see 2x from the original expression there. And that is going to be just log base 3 of 9 plus, right, log base 3 of 2x. Yeah, make sure you know how to do these. Okay, so that means the integral in part II, right, is just going to be the integral of these split terms, right? So integral of log, and log base 3 of 9, isn't it just 2, guys? So it's just integral 2 dx, right? Same bounds here. And then plus integral of that thing we already got from the trapezium rule. Yeah? Okay? So integrating 2, putting the bounds in. So integrating 2, we get 2x, and I put the bounds in. So it's just 9 minus 3 for that, right? And this is just plus the same value we got earlier, so 13.275, yeah? So 9 minus 3 is 6, that's 12, so that's 25.275. That would be my answer there, keeping every decimal place. Okay? And that's it for this whole question, all right? Next, let's have a look at question 9, yeah? Okay, it's a wheel again. The height above the ground, h meters of a passenger on a Ferris wheel, t seconds after the wheel starts turning, is modeled by the equation. So we have a modulus of a trig function. Yeah, so this is probably the only one year that it does this to a trig function here, just putting a modulus in. And then it also gives you like figure 5 here to show a sketch of the graph of h against t for 1 revolution of the wheel. So we need to be careful with this, right? Let me maybe take the graph here to explain a little better there. Okay, just gonna copy the diagram and maybe put it in the working space here as well. Okay, there you go. All right. Now, if you consider the modulus function, right? So the wheel here, yeah, So if you consider this, wait, hang on. If you consider this point, this is when it's like at the almost at the bottom somewhere, right? Or at the start somewhere that is not at the bottom. Okay, actually at the start, t is 1. It says t is 1, right? Here we have the passenger is 1 meter above the ground when the wheel starts turning. So that is just 1. And then the maximum height is 50. So this is actually 50, right? Yeah. And then at some point we have 0. Okay. Now, so let's assume that 1 meter above the ground is, say, maybe somewhere here, right? Maybe somewhere here. Okay, let's say that. So, and let's say that the wheel is turning anti-clockwise, yeah? Because it seems like this is going up. So it's gonna maybe go there first, yeah? To go higher up. So you're gonna get to the maximum point here being 50. And then you're gonna go down, right? Okay? And that's gonna go down. Now, but because this is a sine function, okay? When you deal with the nature of the sine wave, actually, you are having a full sine wave like this. Now, if you consider the normal sine wave or sine curve, it's going to go up and down below the neutral line. But if you look at this, the curve here goes up and down, and if you see the truncated part here, it's still going up in the next period. Of course, that is mimicking the actual situation here where height is always positive, right? So you go from there 1, and then you go to the maximum here, you go down. And although you are at the lowest point, yeah, it's not going to be a negative. But it's actually still progressing along this curve, but because it has the modulus sign here to make it make sense. So when you are actually along this on the actual sign without the modulus sign, it's going to go down, but when you put the modulus in there, it's going to go up. And that is where, like the part of the modulus sign there, right? But the key thing to take here is about the period, okay? But, you know, let's do in order there. So part A, we need to find, we're going to keep this graph for later. So part A, we want to find a complete equation for the model. So we're going to find the A, the B, and the alpha. So let's read in order here. The maximum height of the passenger above the ground is 50 meters. 50 meters, right? So the maximum happens when the whole sine function equals 1 or minus 1, right? So the whole sine function equals 1 or minus 1, well, for, hang on, yeah. So the whole sine function equals 1. So that means h equals A equals 50. So A equals 50 there. Okay? And then the next part is saying that when the passenger is 1 meter above the ground, the wheel starts turning. So the wheel starts turning, that is when we put 0 into the time. Yeah? And then we only get, so we have h equals modulus of 50 now because we already got A. And then sine of alpha. Well, I think we need to solve this later, right? Oh, no, actually we can solve it now. So h is 1 there. Okay. So, yeah, in this case, I think alpha can be either value. So you can do like alpha is 1, like sine alpha, yeah, is equal to plus or minus 1 over 50. So you just solve that. So, I mean, you can try to arc sine. So let's use a calculator there. Arc sine 1 over 50, right? That's in degree. Wait, no, that's not arc. Okay, sorry. Arc sine 1 over 50. Yeah? Yeah, so that is just the alpha there. So alpha is just, we can do plus or minus, right? That doesn't really matter, I think. So we're going to keep everything plus here. That's just 1.14. So the alpha is in 3 significant figures. So I'm just going to go with 1 5 here instead, degrees. All right, so we got the alpha there. And also the last thing is the b. Now we need to consider the periods now, because when you have a normal sine graph, so let's say this is t and this is sine t, so the y-axis is sine t, then you only have you're gonna have a normal sine wave here, nice and easy. And usually we consider degrees, right? So it's gonna be 180 here and 360 here. Okay, now but look at the graph there. It doesn't quite have a full proper sine wave because the sine wave is flipped up here. So the wheel takes 720 seconds here. It's indicating that this period of time is about 720. And if you look at the actual sine wave here, it is just this period right here. Okay? So what's happening here? Half period of the actual sine being 180, but you change it to 720, right? So what happens there? You change it to 720, so that's like multiplying by 4. So I'm saying that that period there, just the half period of the full sine wave, but because we have it like this is only half the wave, right? So this period right here is 720, but in actuality it should have been 180 if not for transformation. But now there is a transformation because we are figuring out the b here. So what do you need to do to go from 180 to 720? Well, you need to multiply by 4, of course, but b is like the opposite, right? So b should be 1 over 4 instead, because then you would do the opposite to the 180 to get it to 720, right? So let's say if b was 4, then it would have given you 180 divided by 4 instead for the period of one turn, but that's not the case. So it should be 1 over 4 so that when you do this transformation, it multiplies by 4 to the 180, so you get 720. So that means b is going to be 1 over 4. And that is everything, right? The alpha, the a, and the b. Okay? And now because we want the whole equation, the complete equation, so h becomes just 50 sine b is 1 over 4 t plus 1.15 in degrees in modulus. Yeah, so that's the complete equation there as well. Part b. Explain why an equation of the form that where d is a positive constant would be a more appropriate model. Okay, so let's have a look. It has the d here. It has the d there. So think about it. Why is there a d here, but the original model doesn't have it? Well, let's have a look at the wheel here again. Well, if you are at your lowest point, yeah, whatever that is, the lowest point this can be is when the sine equals 0. Because it's not going to be minus 1, because when you have a minus 1 from the sine, the modulus will turn it to a positive anyway. So the absolute minimum that you can get from that function is going to be 0. And what's wrong with that? Well, there's a lot wrong with that, because you can't really, think about it. If you are at the point here in the wheel and then you turn down, that can't reach 0, can it? You can't quite be 0. In reality, there is a little height here. Yeah? So we say here that without d, it means that the passenger would reach the ground, i.e. at h equals 0, right? So that's not appropriate. If you go to this Ferris wheel and then you need to reach the ground somehow, somewhere, that's not safe, right? Okay? So that is it for question 9. Next one, question 10. the function f is defined by this. Find f inverse of that. All right, so A, well, that's probably not too bad. The more interesting things are down here actually. So part A, so f inverse. All right, so well, we probably need to find the inverse first, right? So we probably have to do that. Yeah, all right, let's find the inverse first. Is there a quicker way though? I mean, yeah, okay, actually this is like a trick, but let's try put f inverse of that equals y first, and of course we need to find the value of y. Now, but if we play around with the algebra of the function here, we can move the f inverse here to the other side so that we get 3/2 equals f of y. All right? Yeah? Now what's the point? Well, f of y here is, y can be anything. So I could have changed the letter y to an x as well. So let's actually use x, yeah? So let's say the thing we are finding is x, and then that's just fx, right? And there you go, fx is just the whole function. So basically you are just putting 3/2 to that whole thing, yeah, and solve for x, right? And that's easier because then you don't need to find the inverse function, because I don't think you need it later, yeah? So that's it. So we cross multiply, we get 6x plus 9 equals 16x plus 10. It's going to save you some time here. So 10x equals minus 1, so x equals minus 1/10, yeah? Yeah, so that's it. That's the answer there for the first part. Part B show that fx equals a plus b over 2x plus 3, where a and b are constant to be found. Well, this form requires that you do some division here first to get what's called a quotient, being a here, and b would be the remainder. So actually, well, we can just try divide the first term here into the first term. Probably don't need to do the long division there. So a is going to be, so 2 dividing into 8, we get 4, right? Yeah. And that's going to be, so if you multiply 4 to 2x plus 3, you get 8x plus 12, right? And if you subtract 12 from 5, you get minus 7. So this is going to be minus 7 divided by 2x plus 3. And if you're not happy with that, you can try, you know, like multiply this back in, like the cross multiply, make the denominator the same. So you get 8x plus 12 here, and when you add back with minus 7, you get 5, right? So we can just prove that. All right. Now next, part C. Part C, the function g is defined by that. Okay, state the range of g inverse. Okay, the range of g inverse. Now here, let's have a look at the nature of the function. This is a quadratic function and is an inverted parabola shape. So that is having a maximum of 16, right? So we plot a graph a little bit. I mean, it's useful when you know how to plot the graph, right? 16 there, parabola. So you get a quick idea here that the range, so that's go from 0 to 4. So 0 is there. So when x equals 4, y will be 0. Okay, so actually it doesn't have the left part there. We need to maybe delete this part out. Okay, but that's fine, that's still the same. And also the right part of that. Okay, so that's it, 0 to 4. The range of g inverse is going to be the domain of g. Yeah, so range of g inverse is equal to the domain of g equals, what is the domain of g? Well, domain of g, isn't it just that? 0 to 4. So the range of g inverse is then we can just say y less than equal 4 greater than equal 0. Okay, that's part C done. Find the range of f of g inverse. Okay, this is a composite function. Okay, and I'm gonna be thorough with this because I have got some comments requesting me to explain it again. Here I'm going to do it again. The easiest way to work on the range of a composite function without having to derive the expression again. So look, this one you haven't got the expression for f of g inverse. I mean, if you work on the hard way, you would need to get the g inverse, right? The expression, and also plug it back into the fx, and then derive, and then simplify, and that's hard work. How about the easy way? Well, let me show you. The easy way is to just use the domain. Okay, so when you have a normal composite function, okay, I'm just going to write f of g inverse here. Well, this part will become domain first. Okay, so I call it the inner part. Okay, so let's put another brackets in there. This whole part will be domain of the composite function. It actually becomes the domain of the f outside. So the domain of the inner part, the domain of the outer part, yeah, is this whole g inverse of x. And what is g inverse of x? It's just the range of g inverse of x. So it's the domain of f there, but the range of g inverse. So it's like what is the possibility of g inverse of x here being inside the brackets? So if you think about the possibilities of the value that you can plug into this brackets, so-called the domain of f here, we consider the range of this guy, right? And the range of this g inverse of x is already obtained earlier, being from 0 to 4. So whatever expression g inverse of x will be, the output, let's say output, cannot go smaller than 0 or larger than 4, because that's the whole range. So now you have some idea that this, the g inverse of x here is just smaller than 4 or equal larger than 0. Right? That's the whole range of g inverse. So that means, whatever the outer part function is, you can just go like f0 to f4. And that's what gives you the range of this whole composite function, because now you know that the inner part is going in between 0 and 4. So that means the whole output of this composite function cannot go outside f0 and f4. So it should be in between f0 and f4, whatever the value might be. Right? So we consider now, right, if the domain of f is to be between 0 and 4, what is the range we're going to get here? So basically I'm using 0 in between 0 to 4 to be the domain of this original fx, right? So here we already got some idea about what to substitute in to get the range of f of g to get the range of f of g inverse here, right? So if we substitute 0 in, what do we get? So f0 here is just 5/3, right? Let's try substitute 4 in. Equals, what is that? 32 plus 5 divided by 8 plus 3. So that is just 37/11. Now look, some of you might be asking, hey, what about the very upper bound of the whole function when x approaching infinity here? So when x approaches infinity, that's going to go to 4. Because you can ignore the 5 and the 3 here because they would be negligible. So it's just 8/2, right? When x approaches infinity. But we are not dealing with that here. We only have the upper bound of the thing we want inside the f here being 4. Because as I said earlier, you got the idea of this input, yeah, being minimum 0 and 4. So you only consider the domain of f being 0 and 4. 0 gives you this, 4 gives you this. So you already got the range there. So we can write there f of g inverse of x is just going to be in the range of that. Now, can it be 37 over 11? Yeah, because this can be 4, so that can be. Can it be 5 over 3? Yeah, because it can be 0, right? It can be 0 here. So that's going to be also 5 over 3 here with the equal sign. And that is it. That is the range of the composite function there without having to sweat finding the whole expression again. And you should try understand this because it's going to save you a lot of time. All right, so that is my answer there. Next question, question 16. Figure 6 shows a sketch of the curve with parametric equation. All right. Blah, blah, blah. The line L is normal to C at the point P, where T is pi over 4. Using parametric differentiation, show that. Okay, so we are just going to, part A here, we're just going to differentiate first. So dy by dx, that's going to be dy by dt divided by dx by dt, yeah? dy by dt, we need to differentiate the y respect to t. So differentiating sec, we should get sec tan, I believe, right? So just doing the chain rule there. So we differentiate the sec squared, we should bring the 2 down. 2 multiplying 2, we get 4. So 4 sec to the power of 1 first, and then doing the chain rule. So looking at the formula sheet here, yeah, if you differentiating sec, you get sec tan, of course, right? From there, okay? I'm just gonna open the paper back up. So we now have done the outer part, which is to bring 2 down and power minus 1. So the chain rule here is to differentiate the sec t. So we get sec t tan t, right? Okay? And this is all divided by dx by dt. So differentiating tan, we get sec squared. So that's just 2 sec squared t. Okay? The 1 goes away. And the 2 sec cancelled out, we get 2 tan t there. Okay? And then we need to find the normal equation to see. So the dy by dx here will be, for the normal, for the tangent first, will be equal to, because we know that t equals pi over 4 at point P, so we're going to substitute that. Okay, so tan pi over 4 is just tan of 45 degrees, that's just 1, so this is 2. That means the gradient of the normal is just minus 1/2. Okay, that's the gradient of normal. Well, you see it's lurking here already, minus 1/2 there. And we need a point P there. So we need x and y separately to plug into the linear equation and then solve for it. Okay, so x equals 2 tan pi over 4 plus 1. So again, tan pi over 4 is just 1, so that's going to be 3. Y equals 2 sec squared pi over 4 plus 3. Well, cos, right, which is the reciprocal of sec, cos pi over 4 is 1 over root 2. So squared, you get 1 over 2. So flip it, you get 2. So 2 times 2 is 4. 4 plus 3 is 7. Okay, now you can use this form to find the linear equation. So y minus y1 being 7 equals the gradient there, minus 1/2, x minus x1 being 3. We need to do the gradient intercept form there. So I'm just going to do y equals, let's do it on the same page here, y equals minus 1/2 x, and then plus 3 over 2 plus 7. Okay, so minus 1/2 x, that's going to be 7 over 2. Yep, that's right. Okay, that's part A done. Part B, show that all points on C satisfy this equation right here, all points on C. Okay, Well, that is basically just changing the parametric equations to a single Cartesian equation. And this is just for C yet. It's nothing to do with that line yet, with this line. So it's just C itself, yeah? So how do we play with this? Well, I see that there is a tan and a sec squared there. So we connect them. Mostly when you see parametric equations in trig functions, right? Usually the way to go is just to bring up some trig identities. And you have a square here, so think about the square identity, right? So the sine squared plus cos squared equals 1, or the sec squared minus tan squared equals 1, or the cosec squared minus cot squared equals 1, right? So here we go. I'm going to use, so let's make tan t the subject. So I have x minus 1 over 2 equals tan t. Yeah? Just moving the things around there, yeah? On the x part. And then we know that this will be, if we square this, right? If we square this, we get tan squared t, right? Yeah? And we also know that tan squared t is just what? 1 plus sec squared, in it? T. Yeah? No. 1, hang on. Is sec squared minus 1. Yeah. Okay, that's it. That's just tan squared t. Now, but what is sec squared? Sec squared is, if you rearrange the y there, the y part here, you get y minus 3 divided by 2 for the sec squared, right? Yeah, so this is y minus 3 divided by 2 and minus 1. Okay, I'm just rearranging for the sec squared here to be the subject, and I substituted in here. And now we need to work around that. Okay, so let's have a look at the final form here. Well, they keep the x minus 1 squared here, so we don't touch it. So let's say this is, okay, so let's bring 1 over 4 out, and then this is still x minus 1 squared equals, so the whole thing there is just y minus 3 minus 2 there, divided by 2, right? If we multiply by 2 across, then we get 1 over 2 x minus 1 squared. This is equals y minus 5. Okay, equal to y minus 5. All right, and then if we make y the subject, then we should get what they want, which is just to move 5 here instead, as required, right? So that's part B done. So part C here, we need to find the range of possible values of k. Well, they say that the straight line with equation this intersects C at 2 distinct points. Now we already got the curve C in a Cartesian form. Well, we should make use of that. Well, we could do the parametric way, but there's no point now because we already got a better way, which is the y in terms of x function of the C, the Cartesian form. So we're going to equate this curve to this line, and let's see what happens, right? So that's part C there. So minus 1 over 2x plus k equals just that whole curve there. All right. Now, do you see that, well, if we expand everything and then we rearrange it to a quadratic form, and then because this is intersecting at 2 points, and then we can do discriminant, right? Yeah, that's the key way to go there. So I'm just maybe multiplying 2 across here, so I get minus x plus 2k equals, so expanding that, and this is a plus 10 here at the back, right? Yeah. So I get x squared minus 2x plus 1. Already multiplying 2 every term there before expanding that. Move everything on the same side, I get x squared minus x to the right there, and then plus 11 minus 2k equals 0. Yeah? Like that. Let me double check. Yeah, I think I'm happy with that. Okay. Now, we need to use discriminant, right? So b squared minus 4ac would have to be greater than 0 because that's 2 distinct points, right? So b squared is minus 1 squared minus 4, a is 1, c is 11 minus 2k greater than 0. So that's just what, 1 minus 44 plus 8k greater than 0. All right? Yeah? So what do we have here? We have 8k greater than what? 43, right? Moving everything on the other side. So k greater than 43 divided by 8. Now, there is actually a problem, right? So when you think that k can be greater than that, but can it be greater forever? Well, for example, if we draw the graph, right? So the given graph is where the curve is like that, and let's say k is somewhere so that they cut at 2 points. Actually, the curve might also be okay. So let's say it's going to be like this. Yeah, cut at 2 points there. So you see the curve on the left part is truncated at perhaps minus pi over 4 here. That is where it stops there. Stops going further to the left, right? So if we move the line so that you don't have any more intersection on the left part now, it's not going to cut at 2 points. This happens because you have the limited domain there. So the domain doesn't go forever for the x. It's not like a, so if you look at the quadratic function here, yeah, this equation here is the curve equation. It was actually from the parametric curve, and that is truncated. So although in a normal quadratic function, the x doesn't have any limitation, right? But in this case, it does. Okay? So we can't really make the curve go beyond that point right there. This point right here. So we need to know where this is. And that's happened probably when, you know, t equals minus pi over 4 there, because it is specifying the domain there. So let's try put that in, right? So if t is minus pi over 4, x will be just 2 minus 10 of minus pi over 4. So minus will be the quadrant 4. So that's just minus 1. So this is minus 1 plus 1. So that's going to give you minus 1. So yeah, that makes sense. This is x of minus 1. Okay? What's wrong with that? Well, if you put minus 1, so then we now have to find the limit to k here. So k cannot go beyond this point because k, don't forget, is the y-intercept of this line. So k is at that point. Now, but we got to find the actual k. So we know that, let's say it's going to intersect that left wing of the parabola there. So we're going to put this point right here to the same point as in the linear equation. But this point right here is x equals minus 1. What is the y? We don't know the y yet. So let's get the y value of that point by just using the curve equation here. So y is going to be 1 over 2 minus 1 squared plus 5. That is going to be minus 2 squared is 4. So 4 over 2 is 2. So that is 7. So it is at minus 1, 7 there. So if we put minus 1, 7 to the linear equation, we get 7 here equals minus 1 over 2. X is minus 1 and plus k. Yeah? So you're going to get the value of k there. So k is just 7 plus 1 over 2, right? Minus. Yeah? So that would just be 13 over 12 for the value of k. So that means the possible values of k would be k have to be greater than 43 over 8, but less than or equal 13 over 2. We can take an equal here because it can be at this point, so that it still cuts 2 points there with the curve. It has to be greater than this, of course, because we solved it from the discriminant. So there can be no equal sign there. All right? And this will be the answer. All right, guys? Now let's go to the next year, which is June 2023. Okay? Let's look at the first question, which is just question 1. Okay? June 2023, question 1. Find f double dash x. Well, we just find the second derivative here. Now, the reason why I handpicked this one is because I see the thing concave here, which is a jargon there. You just need to know what it is. Yeah, I'm going to explain it in a bit. So let's just do part A first. Let's find the first derivative first, yeah, before you find the second derivative there. So the first derivative, just differentiate it once. We get 3x squared for the first term. The second term, pulling 2 down, we get 4x, and then minus 8. Differentiating it again, we get 6x here plus 4. You should be okay with this, yeah. And then part B. Solve f double dash x being 0. So part I, 6x equals 0. We get x equals minus 2/3, right? Quickly there. Okay. Now for part II, right? Let's understand the jargon concave and convex first. So the easiest way for you to probably remember this, I think, is to think about the cave. Yeah, the cave is like this, isn't it? And maybe there is an entrance for the cave, and that is just mimicking the actual concave concept of the geometry here. So you can see this line, yeah. So the concave is where the curve is kind of like above the line. Yeah, you see this cave like outline, and then the line here is below the outline of the cave. So this is concave. Yeah, it could look like this. So if you have a curve like this, and if you draw between 2 points on the curve, if you draw a straight line, this is also concave because the curved part is above the line. Yeah, but the way you probably remember is maybe to draw a cave, and then there is a door of the cave here, something, and you'll see that the line is below the cave, like the outline. So now how do we use this and then find the range then? I mean, how do we know where to start here? Because we have a cubic curve here. Well, let's get some idea about the cubic curve. So that is just the leading power of 3 there, so that we see that it's a cubic curve. But it's a positive cubic curve because the sign in front of x cubed is just positive. So it's just going to look something like this, yeah? Now, we already solved for the x equals minus 2/3 here being the inflection point, if you don't know that. The inflection point is when the curve changes like the trend of the gradient, if you like. It is this very point right here, around there. It's just where, like, okay, you see that this is totally a curve, right? And this part is totally also a curve, like there is no straight line part here. But at this exact point, this point right here is like the point where it's temporarily being a straight line. It's just like a turning point, but not exactly, because at the turning point is just dy by dx equals 0, but this is d squared y by dx squared being 0. So it's where the gradients start to change. As you can see, this is where gradient starts getting steeper and steeper, right? Or if you like, it's getting smaller and smaller and smaller. So smaller as in more negative, right? But then after this point, it's getting greater and greater and greater, as in being less negative. So that is effectively where the gradient changes. Okay? And that's called inflection there. Now, we know that is the inflection point. Now, where is the concave part then? Well, obviously, the concave part is where you draw a line. Let's say if you want to look at this left part, you draw a line from maybe the left part and to that inflection, because inflection is where it decides whether it's a concave or convex, right? So you see, if you split it into 2 parts, this part is the cave and this part is the convex because the curve is below the line. All right? So I'm saying it splits there at the inflection. That's why it asks you to do the inflection first to solve for f double dash x equals 0. Okay, now this is the concave bit, but Where does it go to the left? Well, it can go in, forever down there. And everything will be concave anyway, because the curve is above the line. Okay? So we already know that this point is where x is minus 2 over 3. Alright, and the curve doesn't stop anywhere, so the concave part is just hence x less than minus 2 over 3. Alright? Okay, so if you draw any line between any 2 points, if you draw the line between any 2 points, the curve is always above the line. Okay? If you do that to this part instead, let's say I take that point and maybe that point, well, the line is above the curve. How about that point and that point? Well, kind of the same, the line above the curve there. So we take the left part where x is less than minus 2 over 3. Okay? Let's go to the next question. Question 2. Okay, question 2 is also interesting. A sequence u1, 2, 3 is defined by that. Part A, I show that u2 is 40. Well, that's not bad because we're just going to plug u1 being 35 in first. So u2 is just u1, right? 35 plus 7 cos n, which is in this case 1, because we are doing n of 1 here. So that's just pi over 2 minus 5 times minus 1 to the power of n, also 1. Yeah, that's u2 there. So that's just 35 plus cos pi over 2 is 0, right? So that's just 0, the whole thing. And this is just plus 5, so that's 40 as required. Part 2. Find the value of u3 and the value of u4. Okay, it's just gonna ask us to find everything there. u3 will then be also 30, no, not 35, now 40. Yeah, because that's u2. And then plus 7 cos n has to be 2 now, 2 pi over 2 minus 5, n has to be 2 now, so that's the power of 2. Cos of pi is just minus 1, so that is just 40 minus 7 and minus 5 there, because that's minus 1 to the 2, become 1. So we have what? 28 for u3, right? And u4 is just, again, u3 plus 7 cos 3 pi over 2 now, minus 5 minus 1 to the power of 3 instead. Okay, so 28 plus, well, cos 3 pi over 2, let's see, so that's the third quadrant. It's like 270 degrees, so that's like 0 still, right? Because cos pi over 2 is 0, so cos 3 pi over 2 is still 0. So this is 0 then, and this is minus 1 times minus 5, so it's a plus 5. So that is 33 for the u4. Given that the sequence is periodic with order 4, so that is saying that there should be 4 unique terms. We have got u1, u2, and u3, and u4. So 4 of them already. So we stop here. Write down the value of u5. Well, that is just to check the understanding, that if you guys understand what it means to be a periodic sequence. Yeah. So u5 is just going to be u1, because there are just 4 unique terms. So u5 will be equal to u1 equals a 35 instead. You can try, go ahead and find u5. You're going to see that it should be 35, right? Part II, and this is the real thing. Okay, so because it's periodic, the summation here we want to find in part 2 from the first term to the 25th term of ur. Well, again, I mentioned this earlier that when you see a sequence like this, don't panic. Just try. I mean, this one is good because you already know that they're going to repeat. You don't need to do any more work now. You have done it. So, because the order of periodicity here is 4, so that means there are sets of 4 unique terms, the same unique terms, right? And if we go in 4s, we're going to be 4, 8, and 12, and 16, and 18, and 22, and then wait, what? hang on. Yeah, if we go in 4, it's going to end up being at 24. Right? Because that 24 is a multiple of 4. So you are going at maximum 6 sets of 4 unique terms, and then have a remainder of 1 left because we have 25 terms here. So it's 6 terms, right? I said 6 times 4 is 24, yeah? And then 4 of them added together in this bracket. So we have U1 being 35 plus U2 being 40, U3 28, and U4 33. And then add another first term, which is 35, to make it 25 terms, right? So we're just going to use a calculator there. So 6 times 33 plus 40 plus 28 plus 33. Yeah? Wait, what? And then plus 35. Nope. 35. Yeah, so that's going to be 851. That's everything, guys. Okay? All right, let's get to the next question, number 9. The curve C has parametric equations that A show that the Cartesian equation for C is that. All right, so Cartesian equation, huh? Okay, so we need to merge the X and the Y here. How are we going to do that? Well, this one, I handpicked it because it's not that easy, right, to get the Cartesian form here. Well, let's see. Okay, so, well, if we complete square, if we notice this is t plus 3, and then if we complete square the x, right, complete the square for the x, so it's going to be t squared plus 6t and plus 9 and minus 25 to get back to minus 16. I add a plus 9 there and compensate it back by minus 25 to make it go back to minus 16. So I'm not changing anything. I'm just manipulating the numbers here. What's the point? Well, because we know that t plus 6t plus 9 is just a complete square of t plus 3 squared there. Okay? Now what's the point? Well, of course, the point is to rearrange so that we know that t plus 3 will be equal to x minus 25 square root, right? And we can't have a negative there because when we, the point here is to substitute it into here, all right? Substitute it into there, okay? Now, okay, here's the deal. Y equals 6 ln of square root, right? Let's do x minus 25 to the power of half here, yeah? It's going to be that. And that can be negative because if it's a negative, then that's going to be an error. It's like, it's undefined, right? Now look, because they have an x plus b here, right? So that means we can't have a square root here. Well, we manipulate because we know that we can spare this 6. Let's say it's a 2 here, 2 ln x minus 5 to the power of 1/2. And then I times 3 out here so that I can do like a 2 and throwing it up so that it multiplies with the power there so that it becomes just x minus 25 without the square root or the power 1/2 there. Okay? So A in this case is 3 and B would be minus 25, right? So A is 3 and B is 25, minus 25 actually, yeah. Okay, x greater than 25. Yeah, that's right. That makes sense. Okay, so that's just the answer to part A. Part B. The curve C cuts the y-axis at point P. All right then. Okay, show that the equation of the tangent to C at P can be written in the form that. Okay. Okay, so the y-axis, yeah, cut the y-axis, you need to get that point, happens at x equals 0. So the x-coordinate of P is just 0. Okay, so we're going to find the x-coordinate of P plugging 0 into the the y-coordinate of P plugging x0 into the equation here. So let's see, we should plug it in here, right? So x equals 0, y is going to be equal to a, which is 3 ln of, wait, what? Y-axis at point P. Oh, I made a mistake. I made a mistake here, guys. Yeah, I see it. Okay, that should be all plus, right? Yeah, and B should be a plus now. All right. Okay. So now it's just y equals 3 ln 25, right? For the y. Yeah, if you make x0, that's just 3 ln 25. Okay, so after we got the y coordinate of P now, we should find the gradient, right? And to do that, we need to differentiate, right? So because we already got the Cartesian form, so yeah, we're just going to do Cartesian. So dy by dx is just, what is that? It's this form right here, right? So it's just differentiating ln is just 1 over the whole thing. And then if you do a chain rule there, that you're just going to get 1. So yeah, it's just 1 there. So that's it. And then we substitute, right? So dy by dx is going to be equal to 3 over x being 0, right? Plus 25. So that's going to be the gradient there of the tangent. And we find the gradient of the tangent here. That's right. We're going to get the equation of the tangent. So we're doing y minus y1 being that, because that is at point P. So equals m x minus x1. So that's just x, because x1 is 0. And then we're going to get the equation into this form. Let's see, it's a ln 5 there. Okay, actually ln 25 can be 2 ln 5, right? So that's y minus 6 ln 5, because 2 multiply 3 there. And then you have 23 over 25x here. Let's see, if I multiply everything by 25, I'm going to get 25y minus, well, 25 times 6 is 150, right? Ln 5 equals 3x. And if I move everything and move ln to the other side, I get, yeah, that's fine. So minus 3x plus 25y equals 150 ln 5. That's just the final form there, guys. All right. Now let's do the next question. Question 12 on the same year here. Okay. Oh, modulus again, right? The number of subscribers, if you haven't subscribed, then please do so, to 2 different music streaming companies is being monitored. All right. The number of subscribers NA in thousands to company A is modeled by the equation that. Okay, so the NA is just the normal V shape there, and the NB is the inverted one. Okay. When T is the time in years since monitoring began. Figure 2 shows a sketch of the graph of NA and the graph of NB over a 5-year period. Okay, so T stops at 5 there. Use the equation of the models to answer part A to D. Part A. Find the initial difference between the number of subscribers to company A and the number of subscribers to company B. The initial difference, right? So we are taking the initial value of both functions. So NA, so at T equals 0, then NA is at, well, putting T equals 0 in there, we have a plus 3 after the absolute there, and plus 4, so that's a 7. And then NB is just putting 0 in there, we get a 6 from the modulus, so that's 8 minus 6 is 2. So the difference, right, is just 7 minus 2 is just 5. So 5 subscribers, 5,000. You got to be careful here. If you say 5, I don't think you're going to get the marks, because they use words to ask you. They don't say what is the difference between NA and NB. They use words. So you got to say 5,000. yeah, subscribers. Yeah, different equals 5,000 subscribers. Okay. When T equals big T, company A reduces subscription prices and the number of subscribers increase. Company A. When T equals T. So company A is this. So it's, well, at first, number of subscribers decreases. Hopefully that's not going to happen to me. And then the price, the number of, when T equals T, company A reduces subscription prices and the number of subscribers increase. So that happens at the vertex here, right, guys? So after that, N increases, as you can see. So at T here must be the vertex of NA, right? Suggest a value of T giving a reason for your answer. Okay, so we think that where is the vertex of NA? So it's just at T equals 3. So T equals 3, and this is 3, the value of T, yeah, we can just say 3, although it's 3 years, but this is asking for the value of T, so we can just don't have the units there. We don't need the units. Okay, the reason being because at the vertex of the NA function, which is at T equals 3 here, the NA increases afterwards. Yeah, it's just the point after which NA increases, basically that. All right, that's what I'm trying to say. Okay, part C. Find the range of values of T for which NA greater than NB. All right, so give me your answer in set notation again. Ooh, okay, so NA greater than NB. NA greater than NB. So we need to find these two intersections, right, guys? And now we need to do it thoroughly, because if you're not careful, you just put everything for all combinations of the modulus functions, you're gonna probably get 4 points, I think. Okay, that can happen too. Now we're gonna thoroughly select for each case the 2 correct lines from both V shapes. For example, let's go with the left part of the intersection here, the left intersection. So for the left intersection, is the negative NA part. So the negative line of the NA wing. So the negative is obtained by just putting a minus sign there in front of the modulus and taking the modulus out, and plus 4 here. We're going to equate that to the positive part of the NB. So the positive part of NB is just 8. Well, we are not going to have a minus here, because if we have a minus here, it's going to be a negative part of NB, but we want the positive part. So that's going to be just positive 2t minus 6. Okay? Yeah, just like putting the minus sign here, so it becomes a positive. So we solve that, yeah? So putting t all together, so this is a minus t on the left, so I'm pulling it to the right, equals 3t here. And then pulling the numbers on the other side, so I have a plus 2 on the right. Then if I move it to the left, I have a minus 2, so this will be 3 plus 4 minus 2. So t here will be 5 over 3, right? Yeah. Okay. And now the other case is when NA is just positive and NB the opposite. So NA positive is, you can just put the minus sign here for the other case, right? And the minus sign here, yeah? So that's just 8 minus 2t minus 6. All right? So we're going to move minus 2t to the right, so this will become 3t. And the numbers to the t to the left and the numbers to the right. So we have a plus 1 on the left, so we subtract 1 to the right, we get 15 here. No, subtract 1 should be 14. wait, hang on. It's already 14 here, and then we minus 1, so we get 13. So that's 13 over 3. Yeah? 14 minus 1. Yeah, okay. So that's it. All right. Now, let's see. So we want the part where NA is greater than NB. So NA greater than NB. NA, right? Greater than NB. Okay, so it's just going to be to the left of this point, but cannot be smaller than 0, of course, because we're talking about time here. And to the right of this point, but cannot be greater than 5, because that's the domain there. All right, in a 5-year period. So the range of NA greater than NB is then at T being greater than 0, of course, but less than or equal. Well, I'm just going to say less than, because at this point there is nothing greater than the other. So what is that again? Is it 5 over 3, right? Yeah, because the other one is greater than 2. Okay. Or, right, the other part can't be 5, or can be 5, yeah, I think. And the lower limit there would just be 13 over 3. Okay, just the other part we got there. But we need to write it in the set notation, I didn't forget. Okay, so set notation is then a set of T where 0 less than T less than 5 over 3, union with a set of T where 13 over 3 less than T less than equal 5. That would be the answer there. Yeah. Okay, and that's just part C done. Part D, state the limitation of the model used for company B. Okay, now to answer D here, we need to probably have a look into more details about the graph of NB. So as you can see, NB is like decreasing, keeps decreasing actually. So although the graph says that this is over a 5-year period, but if you go beyond year 5, then you will see that the graph declines and keeps doing that, and it could reach 0. So this would be a limitation for the model to go over some period beyond 5 years. And we can find that where that is. So if we plug 0 into NB and see what it leads us. So 0 equals 8 minus absolute 2t minus 6 here to get the value of t, right? So that is just 2t minus 6 equals 8 plus or minus 8, right? Yeah, I'm just solving the modulus value there. So 2t equals plus or minus 8 plus 6 divided by 2, just the t there. So t equals plus 8 plus 6 divided by 2 is 7. Minus 8 plus 6 divided by 2 is minus 1, which is not possible for time. We're not going back in time there. Okay, so that means if you go beyond year 7, it's going to intersect the time axis here. Okay, so the limitation of the model used for company B is that the NB will be negative when time is beyond 7 years. Yeah? Or year 7, right? Beyond that, the NB will be negative, which is not realistic, right? We can't have negative time there. Sorry, negative subscribers. Okay. Okay, next question, question 14. Show that the equation blah 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 may be written as that, where A, B, and C are constants to be found. Alright, so 14 part A. Well, my first impression is to maybe expand the tan inside there, but let's see if there's any way better than that. Yeah, so probably expansion is the best way, but yeah, okay. So it's going to be 16. Tan is sine over cos, right? So I'm just going to also substitute that with sine over cos already. And then you multiply with 1 cos here. plus also another 10 to that, so it's 46, and then 10 is sine over cos, yeah, and sine squared here. On the right side I get on the right side I get 8 sine 2 theta plus 8 sine, well, you know what, probably I'm gonna keep the right hand side as is first, not expanding or anything. Okay, now isn't 10 squared plus 1, isn't it just 6 squared, right? Yeah, so I'm going to substitute that with perhaps 6 squared theta, right? Okay, now let's see. Okay, so by the looks of the final required form, we need the sine 2 theta there. Okay, we need to do something with that. We need the sine 2 theta, but we already have the sine 2 theta here on the right side. That means we need to get it on the left side as well, so that when you move the term on the right side to the left side, everything will be factored by sine 2 theta as well. Yeah, so to pose sine 2 theta to all other terms on the left side, we need to manipulate. So like for example, if I see here, this is sine, you can change that to sine 2 theta over 2, right? Because sine times cos times 2 is sine 2 theta, so that would be sine 2 theta over 2 divided by cos theta here. And that term is similarly, we can do the same thing. So, well, I mean, for this one, right, it doesn't seem to have any sine times cos there, but if I add another cos times cos, right, just multiplying in there, so I'm gonna get, so this one will be cos squared and over sine squared here, and then I have sine and cos here, right? So that's gonna be 46 10 squared, right? Yeah, 10 squared there, and then sine 2 theta divided by 2, yeah, because there is a sine times cos there after I do the 10 squared. Okay, and the right hand side is still the same, so let's keep it the same as 8 sine 2 theta 6 squared theta. Okay, now we simplify everything, so as you can see we have an 8 and then cos theta, sorry, 1 over cos, which is sec. I think I'm going to keep it as sec there, and then sine 2 theta here. This one is just 23 10 squared sine 2 theta as well, yeah, and then the right part is just 8 sec squared sine 2 theta. All right, as you can see, if we move everything to the left side, and we can simplify further, so we need to get we see the cos squared there, right? Okay, so if I move everything to the left side and factor sine 2 theta out, right, I'm gonna get here, if I order that, okay, so I'm gonna have I'm gonna do minus 8 sec squared theta first, and then plus 8 sec theta, yeah, and then plus 23 10 squared theta equals 0, right? Just moving everything there. But yeah, or yeah, we'll see. Okay, so by the looks here, it only has a cos there, so this is telling me perhaps that I should multiply everything by a cos squared. So if I multiply everything by a cos squared theta into the brackets, not the sine 2 theta, sine 2 theta is the same, yeah, but if you multiply everything by the cos squared, the sec squared will cancel to 8 minus 8 here, yeah, because cos multiplies sec is 1, and then we have 1 over cos here. If you multiply by cos squared, you're going to have 1 cos left, so that's just plus 8 cos theta. And then for the 10 squared, if I multiply by cos squared, that's going to be 23 sine squared, right, theta equals 0. Well, that's not exactly what it wants yet, because we can use the identity to change from 23 sine squared to cos squared, so let's do that. And I'm just gonna maybe rearrange that as well. So this is 23 and then 1 minus cos squared there, plus 8 cos theta minus 8 equals 0, right? So we can do that again, sine 2 theta. So wrapping up everything, we get a minus 23 cos theta here, cos squared theta. And then we have 23 here, minus 8, so that's the constant term, so that's minus 15 here, sorry, a plus 15 actually, and then we have a plus 8 cos theta here, okay? And then we can make the first term positive maybe, because that looks nicer. So this is, so if I multiply by minus sign on both sides, I get this, and this, and this, yeah? That's it. So that's as required, right? So that's part A done. Part B, we're gonna hence solve for 360 less than x less than 540, that equation, okay? So by the looks, you can see that, well, it's just changing from theta to x directly, and everything else is the same, right? So solving this means that we solve this, yeah? So we're just gonna write, it's actually just sine 2x, what was A again? 23 cos squared theta minus, not theta now, x actually, minus 8 cos x minus 15 equals 0, right? And then, yeah, we just solve separately, right? Consider the right bound here. So we have two cases where sine 2x is 0. And because it's 2x here, we need to modify the range. So that's just 1080 here. And the left bound will just be 720 degrees. Okay, that's the first case. Or the other case is where we solve the quadratic trig function there. So we put this whole thing to 0, right? Now, we put this whole thing to 0. That means we're gonna factorize this first. So maybe I'm gonna do 23 cos x, and then let's see how that goes. And then 1 cos x here, yeah, equals 0. So let's see how that goes. Well, 5 and 3, what about 5 and 3? So 5 and 3 here, no, I don't think so. What about 15 and 1? Yeah, 15 and 1 works. So 15 here and 1 here. And minus goes with the 23, and this is a plus. Yeah, so we get a minus 8 there, right? Okay, so yeah. Now, let's get back to the left case first. The first case, sine 2x equals 0. Well, how do you get sine 2x equals 0 in the range of 720 to 1080? Well, sine 2x equals 0, that means sine, I mean, if you get the very first angle that makes sine 0 is 0, right? But it's not in the range, so we got to keep going. It's 0, 180, no, not in the range. 360, no. 540, no. And going to 720, yeah, so 720 is the first one that works for the 2x. The next one should be 720 plus 180, so that's 900. 900, okay, yeah. And then if you add another 180, you're gonna get 1080, right? Now if we divide by 2 there, we should get the answer. So that's 360, 450, and 540. Now note that it already tells you that x is not equal to 450 somehow in the question, right? So we're going to reject that actually, and we're going to keep the rest, right? Now we solve the other case. So the first case is where cos x is equal to minus 5 over 23. Okay, that should be some answer there. Yeah, let's solve for this one first. So I'm going to get the principal angle called alpha then. It's just arc cos. Note that I'm going to do a positive value here because I want the principal angle in the quadrants. And then after I get that, it's going to be, so this is cos being negative, right? It's just these two guys. And that would be the alpha and another alpha there. All right? And we got to consider the range of 360 to 540, right? So what's that going to be? Well, we got to keep sweeping until we pass the 360 degrees. And that is already one round. So 360, and then we're going to meet this guy and also this guy. So that would be 360 plus 180 and subtract, take away alpha. And this one will be 360 plus 180 plus alpha. That should be fine because 360 to 540, wait, hang on. Oh, 360 plus 180 is already 540, right? So this one won't work, okay? So that means the only solution to x here will be 360 plus alpha minus, wait, hang on, 360 plus 180 minus alpha for that first one, all right? And the other one, 360 plus 180 plus alpha won't work because that's over 540. So we're just going to get that single one. Things in degree here. So 360 plus 180 plus, minus alpha there, which is arc cos in degrees 15 over 25. Yeah. So that's going to be 490. Yeah, I'm just going to do maybe one decimal place. Yeah. 0.7. So that's the first answer from that. And then the second one also cos x equals 1 from this. Yeah. Well, cos equals 1, the only one that cos equals 1 is 0, right? Cos of 0 equals 1. So 0 is the same as 360 if you go round by one loop. Okay, one cycle. So you have 360 here. Okay. Anything else? Well, you got to get the next one would be another 360, which is over the range already. So that is the only answer from cos x equals 1, which we already got here already. Yeah. So that's fine. We conclude that therefore all the answers will be 360, 540, and 490.7. That's the answer there. Okay. So let's go to question 15, which is the next one here. Probably the last one in this paper. A student attempts to answer the following question. Given that x is an obtuse angle, use algebra to prove by contradiction that sine x minus cos x greater than or equal 1. Okay. Student starts proof by assume the negation there, the opposite, the contradicting statement. Sine x minus cos x is less than 1. Note that he takes away the equal sign because to be opposite to greater than or equal to 1, you got to do less than only and take away the equal sign, right? When x is an obtuse angle, okay. So he did square both sides there, and then we need to continue the proof, right? We need to complete the proof. All right, assume that sine x less than 1 when x is an obtuse angle. Okay, we just need to carry on there. And that's it for this paper. It's just 3 marks. All right, so if we expand that, we get sine squared x minus 2 sine x cos x plus cos squared x is less than 1, right? That's just to square both sides. That's fine. And then we can see that sine squared plus cos squared is 1. So I'm going to write here 1 minus. And as you already know also that 2 sine x cos x is sine 2x, right? So I'm just going to do sine 2x here, less than 1. So what do we have here? Sine 2x, if you rearrange, you get greater than 0. Just moving things around there, yeah? Moving things around. Now, let's analyze this because we need this to contradict, right? Okay, it says that when x is an obtuse angle. So x is obtuse. How big is it? Means that x is less than, so x is obtuse means that x is less than 180 but greater than 90, right? This is the second quadrant. So that means 2x, right, is going to be less than 360 but greater than 180. Therefore 2x, the angle 2x is in quadrant 3 or 4, right? Well, sine of this quadrant is negative, isn't it? right? So therefore sine of 2x, which the angle is in quadrant 3 or 4, yeah, it's like the second half of the sine. So if you check this, right, this is 180 here, and this is 360, right? So all the sine here will be negative, right? So sine 2x should be less than 0 because it's a negative value. Well, that contradicts because we have here sine 2x greater than 0. All right, so this contradicts, yeah? Classic, right? So this contradicts the assumption that, I'm just going to write the whole thing, that sine x minus cos x less than 1. So concluding remark, so you write sine x minus cos x greater than 1, yeah? Blah, 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 sine x minus cos x greater than 1. All right, when the angle is obtuse. Yeah, so that's it. Okay, that is the end of the 2023 June. Now, next year is, the next paper is June 2024. And because I already walked through this paper entirely, so I think the only question that I need to still handpick, because I see a spike in the interest of that video, it should be just this circle equation question here. I think other ones are fine. I think this one is probably the most difficult one in the question, particularly question B. All right, so we're gonna walk through this. So June 2024, question 14. Part A, find the coordinates of center C1. That's fine. So we're just gonna complete the square separately. So I would do it like, you know, separating the X group and the Y group first. So I separating them like this, and I move 33 to the other side. I get that. Now you got to think, what numbers do you add so that each of the groups X and Y will be forming a complete square, right? So if you x squared minus 6x, well, the easiest way to think about this number is just to do minus 6 divided by 2 and then square it. So minus 6 divided by 2 is minus 3. So you square it, you get a plus 9. The other one is similar. So 14 divided by 2, you get 7. And you square that, you get plus 49. Well, because these number 9 and number 49 are added, and it would change the equation. So you need to compensate that so that it remains the same thing. So you add that to the other side. So I add 9 and 49 here then to make it the same. Yeah, we're not changing the equation, we're just manipulating it. So the first group is then forming x minus 3 squared, and the second group is forming x plus 7 squared, right? And then the right side there will just be what? 49 minus 33, that's 16, that's 25. Yeah? So that means the coordinates of the center, C1, is just 3 minus 7. Yeah? And the radius of C1, radius, is just root 25, which is 5. All right? So I think I'm done with part A. Let's have a look at the difficult part here, part B. All right? A different circle C2 has the center with coordinates minus 6, minus 8. Has radius k, which is an unknown. Given that C1 and C2 intersect at 2 distinct points, this is the key. B, find the range of values of k, writing your answer in the set notation. So the best way to do this is to get some idea about the two circles. So let's plot it down, right? So the center C1 was at 3 minus 7, right? So 3 maybe around here, minus 7 maybe down here, yeah? And then the radius of C1 is 5, so it's gonna go up just up to minus 2 here. I'm just finding the proximity of this circle here so that I can draw properly. And down here would be maybe minus 12, right? So I'm getting that circle there. This is to the left by 5, so it's a minus 2 here as well. There you go. And this is probably about 8 here. So here we go. Wait, no. It's just going to be like that maybe. Yeah, about that, you know. Yeah, let's make it around there. Maybe there. Okay, you get the idea. You get the idea. All right. All right. So that's circle C1. And now C2. We know that the center is -6, which is around here, and -8, which is probably around here. This is -8, so it's about here. -6 -8. Yeah, I'm gonna need to shrink this whole thing down because just to illustrate clearly, I need to do some animation there. Okay, here we go. Now, you need this circle to intersect at two distinct points, but thinking straight to that might be a little troublesome because you probably don't know where to start. Now, how about just draw a circle? There you go. So I get a circle now, a circle at center -6 -8, -6 -8. There you go. But do you see that this is not intersecting anywhere with the C2, right? So I'm just going to say this is, sorry, C1. So what you need to do is to maybe expand this circle. Aha, now it starts intersecting, right? Starts intersecting now. So that is just the critical point. Just the critical point. But we want it to intersect more than 2 points. Sorry, more than 1 point, which is 2 points here. So it needs to be bigger than that. Bigger than that. Can it be bigger? Yeah, still bigger. And I mean, again, I think I should shrink this whole thing down. And if you keep expanding this, you're going to see that, okay, at that point, it stops intersecting at 2 points. At that point, it starts intersecting. Yeah, if you go beyond that, you're going to start intersecting 2 points. But if you go beyond that, you stop intersecting at 2 points. So you got to be in between this and this, anywhere in between these. Yeah, this circle and this circle. Now, we know the concept now that we need these two cases. So K will be in between that. But what is K exactly? K is the radius, don't forget. So K is the radius. Now, this is the key thing here. Because when you have two circles intersecting like this, touching, so this is where they touch, the radius, yeah, the radii of two circles will be a straight line like that, passing the touching point, the intersection there. All right, that is the key information here, because it allows you to solve for the minimum and the maximum of K. So how? So this is -6 -8, isn't it? No, sorry, it's 3 -7. And this is -6 -8, yeah? Now you know that at the minimum case, yeah, the minimum K, that is the case. So you just find the distance between the two radii, sorry, the two centers. So K minimum there, right? K minimum is going to be, so K minimum plus the radius here. So K is actually the radius of this guy. So that's K minimum, yeah, would be, we need to subtract the distance of these 2 points by the radius of the C1, right, to find K. So the distance of those 2 points will be -6 -3 squared, and then plus -8 -7 squared. Just using a Pythagoras there to find the distance between those two centers. Okay, so that is square root, and I also have to -5 there because that's the radius of C1. So in the square root, I have what? 81 plus 1 there, yeah, -5. So that is just square root of 82 -5, right? Yeah, I'm gonna check that. Yeah, I'm happy with that. And that's K min, right? I don't think we can factorize that. No, it's 41. Yeah, 41 is a prime number. Now that's the K min. Now what about the K max? Yeah, let's go back to the other case where you are going a little beyond that point here. So the K max is just entirely the radius from this to that? Well, it's just this distance here and adding with 2 of that, right? Or we already got this distance before, is the, yeah, okay, we already got this distance before, right? It was this, yeah? Now if we add that with another diameter of the C1, which is 10, right? We're gonna get to the K max case. So let's do that. So the K max would just be the K min there plus 10, which is just root 82 plus 5, okay? Just gonna shrink that down, yeah? Okay, that's fine. Just putting that back, I should be fine. There you go. Okay, so now we have got the 2 bounds of the K. If we want to put this into set notation, what do we have? Well, it's just going to be K, well, set notation. So it's going to be this K where K is in between. Yeah, so we want 2 intersections. That means it can't be at any bound. So it cannot be at root 82 minus 5 or plus 5. It has to be greater only, right? So it's greater than 82 minus 5, but less than root 82 plus 5. That will be the set notation. Okay, and that's it, right?